Like whatever we discuss, it will be more inclined towards end term. Okay. So do
Okay,
not
sir.
worry. This session will definitely be helpful, I hope. And it may not be helpful for you 100%, but it might help you some 50-60%. That I can assure you. Okay.
Okay, sir.
Yeah. And yeah, as the end term weightage has been released, you might know that graph theory has the highest weightage in it. So it was somewhere around 35 to 40. So if you focus more on graph theory, you might score good in end term. Is the CT session got over or is it still going on?
Sir, it is still going on. It might take about 1 to 1.5 more discussion.
1.5 hours.
Yes, approx 1 hour it would take from now.
Oh,
Half of the question paper is not discussed yet.
which Acha, today is mock discussion, is it?
Discussion, yes.
Okay. Okay. So anyway, what I felt is graph theory. There are few concepts that requires a detailed explanation or a detailed. We have to revise those things. But apart from that, all other things are pretty much understandable if you have understood the terminology. The main difficulty comes for those who are seeing the graph theory for the first time. So for them, understanding the terms and everything, degree, coloring, matching, BFS, DFS, Dags. So there are lots of terms involved in this 2 weeks. So you might get confused with this. But those who are aware of this, I don't see any problem in week 10 level. Okay. So let me share my screen. Yeah. Sorry, I can't hear you.
Everyone.
Hello, sir. I have a
Yeah.
question. Is it right time to ask?
Yeah.
Just with regards to the total score of this maths, how is it calculated, sir? If you could give
It
us
was
some insight.
it was given in the handbook, right? Student's handbook. Something
All
like
right, and
0.1 times of graded assignment.
yeah,
And
and
if you
then
have
point
given
two of which one?
yeah. So if you have given both the quizzes, then we will consider 0.2% of quiz 1 and 0.2% of quiz 2. Is that correct? Even I am not that sure about this.
And the
And
total score should be above 50,
40.
sir, in order to clear
Yeah.
this exam, or?
Yeah, 50, I hope. See, it was way long ago. I have seen this. Let me reopen that and look into that.
No problem. Thank you.
Yeah.
So I have a doubt in mock 7.
Yeah.
Will you be taking doubts at the end of the session or?
You have to get 40%, I hope. More than 40.
More than 40, sir.
Mm-hmm.
Okay. Regardless how many subjects you're taking, if you're above 40,
Each subject is calculated separately.
All right, sir.
And
And you
in
have to
each
score
subject,
above
you have to
40.
get, above 40 in each of the subjects.
All right, sir.
Including all three exam, no? Quiz 1, quiz 2, in term.
Yeah, quiz 1, quiz 2, end term, including all three, you have to score more than 40%.
Not individual. If someone individually fail, then okay.
quiz and quiz 2 are okay, but not end term, I guess.
Okay, end term must be passed, everyone.
End term they should pass with 40%. And overall 50 or 40, I'm not sure. Okay. So just confirm, open the student handbook. It was clearly written in that. You should be understanding it easily.
Sir, can we start with the revisions first?
Yeah.
And sir, does it affect our total mark sheet if someone fail? It will be shown backlog, something like that.
No, I don't think so.
Sir,
I
sorry.
have some doubts
I've
in
just
mock 8, sir.
And
You
sir,
have doubt in?
this session is doubt
Mock
session
8.
only, or
Mock
we will
8.
discussing all concept.
Sorry. If multiple people talk, I can't hear any one of you.
Sir, this
Can it be
session is
one-to-one?
for doubt solving, or first all concept will be covered.
Graph theory will be covered. This is the third session. Okay. So already 2 revision sessions are done. And this
Sir,
was the
for week
third
10
session.
and 11.
Week 10 and 11. And later I can take mock questions, whatever. It will be open. Like as this is the last session you are going to have with us. So for the first 1.5 hour or 2 hours, I am going to discuss graph theory, most important topics of graph theory with an example. And later, last half an hour or 1 hour, I will just make it open.
Okay, sir, you have said that there was previous session, but for week 10 and 11, this is the first session, no? Revision.
Previous 2 revision sessions are of week 1 to 6, and other session is for calculus. And this is the third session.
Okay, sir. Okay.
Okay. Yeah.
I have a
Okay.
small question. In the we have given practice assignment bonus marks, right? In this one grading document, it was showing that 5 marks are for practice assignment bonus and 5 marks are for mock test bonus. But
Is it for
actually,
max one?
no, not for every subject. It is commonly given.
Okay.
But what happened is we have finished all the practice assignments and there was nothing pending, but it is still showing practice assignment bonus marks allotted are 3 only. So
Yes, sir, the same issue I'm having also.
Actually,
Yes, sir,
Can
I
you
also
write
got
this to
only 3
support?
marks.
Yeah. Can you write this to support?
I have called support also and asked. They are just saying to check the grading document. That's it.
No, I think the deadline for completing 9 to 12 weeks is still not over.
Yeah, that is the reason. It
Yes.
is given up to
Maybe.
1 to 8.
In term, we will.
No. Actually, one teacher, I think CT teacher, has, I do not remember who said, but the participation mark, the course participation mark will be including after first term. Sorry, after foundation level. I think so. It will not be including for it. It will not be applicable for us.
No, it is given in the dashboard. 1 to 4, 1.5 marks, and later on, 5 to 8,
know that, but
1.5.
sir has told explicitly. I mentioned that also.
Okay.
Okay. Done. Okay. I request everyone now just be in this graph theory world. Okay. So don't go here and there for the first 1.5 hour. So whatever I speak or whatever you wanted to speak, let us keep it in week 10 and 11. Because it will be difficult to cover all the things. It may affect you only. That is why. So let us have a very good interactive session from now onwards. And I request everyone, if you have any doubts, we can have it at the end of the session. So I will be open. I will be here till maybe it went for 11 or 11:30 or even 12. Okay. Until I clear everyone doubt, I won't leave. So that I can assure you. But for the first 1.5 hour, I request everyone, please be on this graph theory world. So in mathematical world, be in this graph theory country. Clear? Is that
Yes,
okay?
sir.
Yes, sir.
Yes, sir.
Please.
Yes, sir.
Yes, sir, yes, sir.
Yeah. So today I am going to discuss these things. So let us discuss what is this degree, in degree, out degree. And I'm not going to start with the basic graph. What is graph? So by now you should be able to know what is graph, what is path, everything, the terms, terminologies. So we will start directly from what is a degree, what is in degree, out degree. And then we will look at adjacency matrix. And I'm not going to cover adjacency list also. So adjacency list, you can go back and watch, but I will cover how we can draw, what is adjacency matrix and how is graph related to adjacency matrix. Can we compute adjacency matrix if a graph is given to us, or if an adjacency matrix is given to us, is it same as we got the graph? So like this, and then we will discuss vertex coloring. Okay, and then we will discuss vertex cover, minimum vertex cover, and I'm not going to cover maximum independent set. You can watch it later. And then we will look at matching. So what is matching again with an example. And then we will cover BFS and DFS. And also in this BFS and DFS, if an original graph is given to us, how can we draw the BFS tree and BFS tree and DFS tree? So I'm not going to come from backward. Yeah.
Sir, actually, if the BFS tree is given, how to get the original identify the original graph? I had a doubt in the mock paper.
Okay. Then what I will do is I will also say the backward thing also. When a BFS and DFS is given to us, how can we predict the original graph?
Okay, sir. Thank you.
Yeah. So that we will look at, and then I will move to Dags. And in Dags, we will see the topological sorting and longest path. So we will see both of them with an example, direct example. Again, so everything which we are going to revise, I'm not going to give the definitions and anything. So I will give the definition orally, and we will take an example. And if an example is given, if a question is given to us like this, how can we solve that particular question? So what are the tricks? What is step 1, step 2, and how can we achieve the final answer? So these are the things we are going to do today. And then we will look at what are weighted graphs. Okay, and then I will discuss this Dijkstra's algorithm. Discussing means with an example. So we will take an example and solve that particular problem using this Dijkstra's algorithm. And then I am not going to discuss Bellman-Ford and Floyd-Warshall. So if you want Floyd-Warshall, I already have taken a session in week 11. So it was open. If you want Floyd-Warshall explanation in detail, if I take, I will tell you the reasons. If I take Floyd-Warshall in this particular session, Floyd-Warshall will definitely kill me 30 minutes, more than 30 minutes of time. And I will be missing the most important topics to be discussed later.
So is there any question from Floyd-Warshall?
That I shouldn't say, but whatever I am discussing it today, those are most important things. You should definitely go through these things. Okay. Yeah.
Yes.
So and then.
Sir, I am having doubt in mock paper.
If you have doubts in mock paper, while the concept is going or when the concept, so whenever we reach, if you have doubt in week 10 somewhere.
But sir, they are from previous week. So sir, if possible, can you take it in the beginning?
Yeah. So once I am done with graph theory, once we are done with graph theory, then I will go back to calculus and I will just make it open. Okay. It's not like you have to ask questions in graph theory. So it was a complete open session where you can ask from week 1 to week 12. Is that clear?
Yes, sir.
Okay. And finally, we will solve good problems on MCST with examples.
Sir, these notes will be given to us.
These notes, I will send it and they will upload it by tomorrow morning. I will make sure that they will upload it by tomorrow morning. Okay.
Okay, sir. Under supplementary content.
But I also suggest you, if you want the ready right away after this session or during the session itself, I request everyone to take screenshots if you wish to. See, we can't say what will happen tomorrow. I will send it anyway, but I don't know. I can't assure you 100% that they will upload like this. 99% I will make them to upload it by tomorrow morning. If something has happened, you see, Chennai, it is raining and there might be power cuts and whatnot. Anything can happen within these 12 hours. So that is why I suggest everyone who are in this session, if you want the right away notes, please take the screenshots.
Sorry, YouTube will not be available.
YouTube is also available. Anyway, we are streaming this on YouTube.
Link is not there in YouTube.
Link is not there, is it?
Yes,
sir. Tutorial is not uploaded. Link is there, sir.
It is available in the calendar.
Yeah.
Yeah, it is available in the calendar.
Okay.
Yeah, they updated.
Yeah, they updated. Just look at YouTube link. There is a YouTube link. Or else I will just post that. I'll just copy it.
Okay.
Just a second.
Sir, can you please take the Riemann sum concept here?
Yeah, they updated.
Someone saying something?
Sir, I am telling to take the Riemann sum concept here.
It is not clear. Can you can you? Hello?
Riemann sum he wants.
Okay. So Riemann sum I will discuss at the end. Okay. So this was the YouTube link.
Thank you, sir.
Yeah. So is my screen visible to everyone?
Yes, sir.
Yes, sir.
Yes,
Right?
Yes,
Okay.
sir. Yes, sir. Yes, sir.
Okay. Okay, let me start then. So we will start with the degree of a vertex. So always remember, degree refers to a vertex in a graph. So it doesn't refer to any edge or something. So it always refers to a vertex. So when I say degree, it refers to a vertex, particular vertex. So what is this degree of a vertex is? It is just the number of incident edges. Okay, number of edges that are incident to a vertex U is called the degree of vertex U, and this particular thing is only valid in the undirected graphs. So when I say degree we can call a degree of a vertex, we can only use when the graph is undirected. Okay, so if the graph is directed, so there is no term called degree of a vertex in a directed graph. So degree of a vertex always comes in regards of undirected graphs only. So if there is an undirected graph like this, with 4 vertices and some 4 edges, so the degree of vertex A, so degree of vertex A will be the number of edges that are incident. Incident meaning
Connected.
One of the endpoint of the edge is that particular vertex. So it's like this edge is incident to this vertex. So one endpoint of this edge is vertex A. So this vertex A is incident to this edge. Okay. So we will use incident between edge and vertex. So this incident comes between vertex and edge. So between vertex and edge, we are going to use incident, and adjacent we will use between two vertices. So if I say A and B are adjacent to each other, that means there is a direct edge connecting A and B, vertex A and B. So vertex A is adjacent to vertex B, and vertex A is incident to this edge AB. Okay, remember, don't use adjacent in place of incident and incident in place of adjacent, and also don't confuse when incident is given in the question, don't confuse that it is referring to some adjacency between two vertices. Okay, so now you have to just count the number of edges that are incident to vertex A. So here in this particular graph, there are two edges that are incident to vertex A. Therefore, the degree of A will be 2. And what will be the degree of B?
3.
2.
3. So 3.
Yes.
So 3 edges are incident. And C?
2.
2.
D?
1.
1.
And yeah. So this is how you can compute degrees of each and every vertex in a given graph. And if you observe, this is one remark you have to make. If I add all the degrees of all the vertices, so like 1 plus 2 plus 2 plus 3. So what am I going to get?
Even number.
8. Yeah. So which is even number, as well as this 8. If you see, this 8 is nothing but 2 times of number of edges in this particular graph. So how many edges are there? 1, 2,
4.
3, 4. So 2 times 4. Okay. Not only in this graph, the remark is actually sum of degree of all the vertices will be equal to twice the cardinality of edge set or number of edges. So this is referring to number of edges in the graph. So this will hold. This is an important lemma called handshaking lemma. So where this lemma says, if you add all the degree of all the vertices in your graph, it will give me twice the number of edges in the graph, and it is easy to look. So one particular edge will correspond to 2 degrees. So it will add 1 degree to vertex B and 1 degree to vertex C. So each and every edge will give 2 degrees to the graph. So therefore, the total number of edges times 2 will give you the sum of degrees of all the vertices. Okay. So this is about degree, and degree will only come if the graph is undirected. So this is very, very important. And what if the graph is directed?
Sir, one question, sir. Sir, sum of degree of all vertices you told, sir, means for that means every vertex should be connected to the other vertex, right?
Every vertex degree.
Every vertex should have connection with the other vertex.
No, not required.
Not be.
Sir, then in this case, sir, the graph which you have drawn. Sir,
okay, consider this graph. What will be the degree of A?
2, sir.
2. B?
2.
C?
2.
And D?
0.
So D is not connected to to any of the vertex.
Yes,
right? Look at the sum of degrees of all the vertices. 6. And how many number of edges are there?
3 to 2.
So 2 times 3 will give us
6.
6, which is the sum of. So it's not required. So even the graph is disconnected. So this is a disconnected graph.
Sir, at last, can we do some questions related to this topic?
This topic, degree?
No, sir.
The whole graph theory.
Graphing, whole graph theory.
While I discuss concept itself, I will discuss with an example only.
Okay, sir.
Okay, sir. Thank you.
Yeah.
Thank you, sir.
So it's not like I already told, right? I'm not going to discuss concepts more and less examples. Rather, I will take more examples and solve.
Okay, sir.
Okay. Okay. So when the graph is directed, what do we call? So do we call degree or something else? So if the graph is
In degree, out degree.
In degree, out degree.
Out degree.
Correct. So in the case of directed graphs, so each vertex is associated with two numbers, which are one is in degree and the other one is out degree. Okay. So each and every vertex will now have in degree and out degree. So what is this in degree is? In degree is basically number of edges that are coming towards that vertex. Okay. So you have to count number of incoming edges or number of edges that are coming towards the vertex. And out degree is number of edges
coming out from the vertex.
Yeah, that are going away. Okay. So going away from that vertex. Okay. So you have to count. Here also, it in degree and out degree, again, it's just the number of edges you have to count. But in a directed graphs, we will have outgoing edges and incoming edges. So that is why in degree will be separately. We will call in degree. We will make in degree separate and out degree separate, and we will call in degree by counting number of edges that are coming towards that vertex, and out degree is just the going away number of edges that are going away. So the same. Let us take a small example again. So just to make this in degree out degree clear. D. Okay, so let us take this is the graph and let us compute. Now each and every vertex will have two numbers. Initially in undirected graphs we have only one number, and that particular number is just the degree. But right now we have two numbers, which is one represents in degree, another represents out degree. So let me take a black number as in degree and red as out degree. Okay, let us compute in degrees for all the vertex. Then we can compute out degrees for all the other vertex. So now in degree of vertex A. So let us compute in degree of vertex A. So what you have to do is, so number of edges that are coming towards. So this arrow represents the edges coming towards B, and this edge is going away from A. So therefore there are no incoming edges to A. So in degree will be 0. So for B, in degree will be 1. So because one edge is coming towards B. So C,
1, 2,
C,
no sir, 1,
3.
4.
3,
4.
Yeah, 4. So this edge is coming towards C, this edge is coming towards C, this and this. So 4.
Oh, yes,
D,
sir. Incoming, yes.
1.
Incoming.
1.
And E,
1.
F,
1.
1.
Okay. Let us compute out degrees now. Out degree of A will be
3.
3. So now you have to look for edges that are going away from A. So this is going away from A, away from A, away from A. So there are 3. So out degree of B?
1.
1.
So you see this. Out degree of C?
1.
1.
D?
1.
E?
1.
1.
F?
1.
1.
So it is going away. Okay. So you see here, this is how you can compute the in degree and out degree. And here also there is one note. So this is a strong note. So in degree plus out degree is equals to degree
of one vertex, right?
So that is what I am going to say. So this is not equal.
Yes.
So there is nothing called in degree plus out degree is degree of a vertex in directed graph. Okay, and I said this is strong note because this is a blunder in regards of graph theory. So there is no in degree plus out degree thing in directed graphs. So degree always refers to undirected graph, and in degree and out degree refers to directed graphs. Okay, so this is a strong note. Even though I emphasize more on this, I guess 10% of those who are giving n term will definitely do wrong. Okay.
Okay, sir.
Yeah, let's move. So this is about degree, in degree and out degree. So let us look at adjacency matrix. Okay. So what is this adjacency matrix? Adjacency matrix is simply another way of representing a graph. Okay, it is simply another way of representing, because see, if I give directly graph to the machine or computer, it will not understand. So you have to make sure that machine understands the graph. So that is why we give the graph as in terms of adjacency matrix. So then if you give in terms of adjacency matrix, then machine will also understand, okay, so these many nodes are there. So the edges are from this vertex to that vertex and everything. So in order to communicate between machine and you, we will use adjacency matrix. Graph is for us and adjacency matrix is for machine. So that is just another way of representing. And how do we represent it? So if I have a graph, so let me take the graph now. So let me use, okay, let me use 0 numerical number. 1. Okay, so let us say this is the graph given to us, and we have to find the adjacency matrix, corresponding adjacency matrix that represents the same graph. So what should we do? So adjacency matrix, again, adjacency matrix contains only 0 and 1 as the entry values. So it will not contain any values like 2, 3, 4 or something else. So as of now, so
it is not directed.
So it is undirected.
Okay, sir.
Okay, I will take example of directed also.
Sir, for undirected we get symmetrical, right, sir? Undirected we get symmetrical, and directed we get.
Directed we won't get the symmetric.
Sir, but on this graph, sir, there it will be crossing, no? The lines will be crossing. If you, I mean, this is not a planar graph, right? Because
this is a planar graph. I didn't
sir,
draw in that manner.
If you,
I can,
sir, sorry.
If I want to make this planar, I will draw like this. This is planar.
But 0 to 4.
Yeah, 0 to
Acha,
4
nahi,
is
okay. Sorry to disturb.
okay. Yeah. So in order to draw the corresponding adjacency matrix, what we will do is we will just count the number of vertices first. So how many number of vertices are there?
4,
4,
5.
5.
5.
4,
So
5.
we will take 5 rows and 5 columns matrix. So this will be a 5 cross 5. So 5 rows and 5 columns. So rows and columns. And each row represents a vertex and each column also represents a vertex. Like this, row 1 represents 0, row 2 represents 1, 2, 3, 4. Again 0, 1, 2, 3, 4. Now I have to enter 25 entries, 25 values. So this particular matrix will contain 25 values and all the 25 values will either be 0 or 1. So it will take 0 when there is no direct edge from row vertex to the column vertex. Okay, so now you see, let me fill one row, you will understand. So I hope most of you know this, but anyway, I'm just giving this. So 0, so this 0 vertex having an edge with 0 vertex. So if you see, there is no edge that is coming, that is connected between 0 to 0. So the entry will be 0 because there is no edge. And I will give the entry value as 1 if there is an edge connecting those two vertices. So here, this particular vertex 0 and this particular vertex 1. So if there is an edge between 0 and 1, then I will give the entry value as 1 or else I will give 0. So let me check the graph. In the graph, there is a direct edge connecting vertex 0 and vertex 1. So this particular row 1, column 2 value will be 1. So as this is an undirected graph, while you enter the value of ith row jth column, so whatever the value is there for ith row jth column, the same value will be there for jth row ith column. So I mean, now we got value 1 for the entry first row second column. So the same value will be there for second row first column. Okay, so the second row first column is 1 to 0. So this will also be 1. So like this, I can fill the table. So if it is undirected, so the graph, it is enough to fill these values. The rest will be like just the reflection of those values. So let us complete this graph and try to understand how this is happening. So 0, so now row 1, column 3, that is between, is there an edge between 0 and 2? If yes, the value will be 1. If no, the value will be 0. So 0 and 2, yes, there is an edge. So the value will be 1. So similarly 0, 3. So the next entry is 0, 3. Is there an edge between 0, 3? Direct edge. So there is no direct edge. So it will be 0. 0, 4. So there is an edge. The entry value will be 1. So as we have filled the first row, you see the first row order will be same as the first column order. So now you can check it like this. So from, is there an edge from 2 to 0? As this is undirected, if there is an edge from 0 to 2, then there is an edge from 2 to 0. So vice versa. So there, so 2 to 0 is also there is an edge. So the entry value will be 1. So this is what it will be. So if there is an edge from 0 to 2, then there will be an edge from 2 to 0. So if there is an edge from ith row to jth column, then there will be an edge from jth row to ith column entry, ith column vertex. Okay, so that is why it will be the same. So 0, 0, 1. So you can fill it. So next go to row 2 and fill it how we fill the row 1. So 1, 0, there is an edge. 1, 1, there is no edge. So there is no edge from 1 to 1. So it will be 0. So and if you observe, for a simple graphs, all the diagonal entries will be 0. So simple graphs means there are no loops like this. So having like this. So there is an edge going from the same vertex to the same vertex. So that is called as loop. and we are not going to deal with loops. So that is why the diagonal entries will be 0. And if there is an edge between from 1 to 2, then I will give 1, entry value will be 1 or else 0. So there is no edge between 1 and 2, so this will be 0. And there is no edge between 1 and 3, this will be 0. And there is no edge, oh, okay. There is an edge between 1 and 3, so the entry will be 1. And there is no edge between 1 and 4, it will be 0. So the second row will, as it is, copy paste to column, same column. So 1 0 0 1 0. So this you can do only for undirected graphs. Again, from 2 to 3 there is an edge, so the entry will be 1. 2 to 4 there is an edge, entry will be 1. And again, once you fill the third row, you can fill the third column also. And now move to the next row. So 3 to, already these all things are filled, just you have to fill, is there an edge from 3 to 4? So no edge, so the entry value will be 0. So if this is 0, this will also be 0. And for an undirected graph, the adjacency matrix will be symmetric. So you see, symmetric means symmetric along the diagonal. So this is called symmetric matrix. Okay. So why we call this as symmetric matrix is because if you rotate along this axis, this diagonal axis, you will get the same matrix again. So whatever the value is here, it will be there. Whatever the value is here, it will be there. So it's like a mirror image. So this side will be the mirror image to this side and vice versa. So this is called symmetricness. And by looking at the adjacency matrix itself, you can guess whether it is representing an undirected graph or directed graph. If it is not symmetric, it will not be a undirected graph. If it is symmetric, it is an undirected graph. That's it. And now, can we go from adjacency matrix to graph? Yes,
Yes,
no?
sir.
Yes,
Yes,
right?
yes, sir.
Yes, sir.
So this example we will take for
For
directed.
directed.
Yeah. So let me give you the adjacency matrix. And let's see, can you compute the graph? Can you draw the graph?
You will give first graph, then we will plot a matrix. Yeah.
What?
So you will give graph, then we will mark matrix, or you will give matrix, then we will
I
make
will
a
give
graph.
the matrix now.
Okay.
Just one clarification, sir. Non-planar graphs cannot be represented in the matrix.
No, nothing like that.
Okay.
You can represent.
Okay.
Okay. So this is the graph. Yeah.
It should be symmetric now.
Why it should be symmetric?
No, if it is okay, then it is undirected, I think.
Yeah. So just now we said, right? Just look if it is symmetric or not. If it is not symmetric, then it is a directed graph. Okay.
Not symmetric.
So now what should be the approach? What should be the step 1?
Row by row.
Yeah. Now you have to draw the graph, right? So in
So
order to
all
draw
the
the graph, we will
Mark are the vertices.
Mark all the vertices.
Yeah. In a circular manner, it will be easier if you plot it in a circular manner. So A, B, C, D, and E. Okay. So once after having our vertices now we are at to draw the edges. So how we will draw the edges? By looking at the matrix, we came to know that this is not an undirected graph. So there will be a direction to each and every edge. So some edges can be bidirectional also. So that we will see now. But let us try to draw the graph. So what you have to do? Again, you have to go through rows or columns. Let us start from rows. So for a directed graph, the edge will be from this vertex to this vertex. Okay, from row vertex to column vertex. So now you see there is a non-zero. Look out for the non-zero entries. So here is the first non-zero entry, which is from A to B. Okay, so there is an edge from A to B. So from A to B means there is an outgoing edge from A and an incoming edge to B. Okay, so this particular edge we have drawn from this entry value. Similarly, from A, and we will look out for the next non-zero entry. So here is the next non-zero entry. So from A to D there is an edge. So from A to D. So we are done with row 1. Next we will move to row 2. So from B, the non-zero entry is here. From B to C. So there is an edge from B to C. And from B to D there is an edge. So from B to D. Okay. So we are done with all the non-zero entries of row 2 also. Now move to row 3. So from C, there is an edge to A. So from C, there is an edge to A. And next non-zero entry comes here. So from C, there is an edge to E. Okay. So we are done with row 3 also. Next move to row 4. So now from D, we are looking edges from D, going away from D. So then here is the first non-zero entry. So from D to B, there is an edge. So you see here, there is an edge from B to D. Now there is an edge from D to B also. So no need to draw separately. So even though you draw separately, you can combine it like this. So it's a bidirectional edge. Okay, this represents a bidirectional edge. Okay, so this is like this. And next is from D, there is an edge to E. So this. And next we are done with row 4. We will move to row 5. And from E, there is an edge to A. And from E, there is an edge to B. So E to A and E to B. Okay. So these both are same. Okay. So even I represent it like this or like this, both are same. Both are referring to this graph, this particular graph having 5 vertices and some edges, some directed edges. So directed graph with 5 vertices. Okay. Now everyone understood how you can draw a graph from adjacency matrix?
Yes, sir.
Yes, sir.
Yes, right. If an adjacency matrix is given to you, can you identify whether it is undirected or directed first of all?
Yes, sir.
Yes, sir.
Yes. So after identifying, can you draw the graph?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, right.
Sir,
Oh,
can I ask a doubt?
yeah.
Sir, if it is a bidirectional edge, is there anything wrong if we draw it separately, or it has to be drawn like this only?
No, if you draw it separately also, it's fine.
Okay, thank you, sir.
Okay, yeah.
But sir,
So
this
instead of
bidirectional edge within a directed graph, is this a possible scenario?
yeah, it is possible scenario.
And if in case of weighted graphs and all, this might become.
In case of weighted graphs, it's not allowed.
Okay, okay.
Okay, yeah, we will discuss that why is it not allowed. Okay, so right now just be sure that if an adjacency matrix is given to you, whether you are able to identify is it undirected or directed. So after identifying, can you draw the corresponding graph or not?
Okay, sir. Okay.
Okay, yeah. So after getting the graph, again you can compute the in degrees, out degrees, everything, right?
Yes, sir.
But degrees for a directed?
like if you got the undirected graph,
Okay,
then
okay,
you can
fine.
compute
Okay,
the
okay,
degrees.
okay,
If you
okay.
got the directed graphs, you can compute in degrees and out degrees.
Okay, sir.
And again, the reachabilities and everything you can see. So I'm not going to discuss those things. Okay, path,
No.
reachabilities. So everything you know, right? Once you have the graph, you can check the reachabilities. So is there a path from A to E or something like this? If the questions are like this, you can answer, right?
Yes,
Yes,
sir.
Yeah. So
Sir,
that basic
sir,
things I'm not going to cover now. Yeah.
sir, we can also check in degree and out degree using this table,
This
matrix
table
table.
itself, you can, you can see if you add the row corresponding row, what will you get is the out degree.
Out degrees.
Yeah. So if you add all,
Yes.
so
Sir,
let me write here.
topological sort and reachability are same.
No. So if you add all this, what will I get? I'll get 2, and this 2 is out degree of A. Okay, out degree of A. So again, you can check it after drawing the graph. So you see there are 2 edges that are going away from A. So the out degree of A will be 2. So, and the column will represent the in degree. So if you sum the column, even again I will get 2, and this will represent in degree of A. So you can see there are 2 incoming edges to A. So in degree and out degree both are 2 and 2. Okay, you can check for other vertices also. So you can check that. So take the corresponding row. So if you want to get the out degree of vertex C, so go to the row C. So you will get it as 2. So 2 will be the out degree of vertex C. So 2 edges are going away from C. So 2 will be the out degree. So like this. So you can directly get from the graph, directly get from the adjacency matrix. But for more clarity or anything, if you can able to draw the graph, and from graph, you can easily get the in degrees and out degrees also. Okay.
Yes.
Yeah.
So
that is about.
I have a request for you. Means I have a doubt. I want the A square matrix. I don't want the whole, but only one row. So because I know that, but in one question I have done wrong. So I wanted.
You want the A square matrix, is it?
Yes, sir. Only one row you can compute, and all of that I'll do that.
Okay. So okay. Let me do that.
Sir.
Multiplication also here. Yeah.
So you said that the total degree will not be equal to in degree plus out degree.
Yeah.
So how will we calculate the degree?
There is no degree at all in a directed graph. So I
have
told
two
this.
degree.
I already told this, and see, this is how it will be. I just now mentioned it is blunder.
Yes, there is no term in directed graph degree.
In an indirected graph, there is nothing called degree. So we will always separately look at in degree and out degree.
सर एग्जाम में भी यही पूछा जाएगा इन डिग्री कौन सी आउट डिग्री कौन सी है डिग्री नहीं पूछा जाएगा डायरेक्ट
or directed.
See, if we ask the question like degree of an directed graph, then that is an add score to you. Okay, I am saying right now. Okay, and also you can complain on.
What did you say, sir? I didn't get you.
If we had given in the NTM QP saying the degree of a directed graph vertex, degree of a vertex in a directed graph.
Okay.
Then that particular question is an add score to you.
Oh,
or we will give twice of the marks of the score.
Okay.
Okay.
सर कह रहे हैं कि अगर 4 मार्क्स होगा तो मैं 4 मार्क्स मिल जाएंगे.
हाँ 4 अगर चाहिए तो 8 मार्क में दे देंगे. Twice of the question total. Okay. Okay. There is no degree term. So make sure. So don't see why I am stressing this, because so now you are going to complete max 1, and in max 1 you have learned about graph theory. And अगर आपने placements के सामने बैठने के बाद, if someone asks you like basic question like what is the degree of a directed graph, the vertex of a directed graph, so you will be like a number of edges that are connected to or incident to. So he will look at like, have you done max 1 course or have you done graph theory at all? So you shouldn't be like that. So basic things you should always remember. And also the reason behind why there is no degree, because see, there are many lemmas and properties on degree, and all that properties will get what we say contradicted if we talk degree for an directed graph. So there is no handshaking lemma at all. So if so you can check. You treat degree as in degree plus out degree.
Sir, I had one question, sir.
Hmm.
Sir, you said can we sit for placements after math 1?
Not after math 1, man.
I mean,
BS
after completing the foundation, we can sit
diploma.
for.
No, not after foundation also. After diploma,
Oh,
you will be given internships, and then if they like it, they will be taking you as a permanent employee.
Oh, thank you.
Okay.
After what you said?
After diploma. I already requested you guys. So okay, it's my thing. I bought it now, but okay, let's leave those things for the time being, and we will discuss all these things at the end. Okay, we will have some fun at the end. But right now, I have to complete many things.
Yes, yes.
Okay.
Yes, and sir, what is a square represent? A square a to the power 4.
A square represents all the two length paths. Okay. So what will A represent? Adjacency matrix. What will adjacency matrix represent?
One step path only.
Adjacent vertices, right? Neighbors, right? It will give us the neighbors. Neighbors means what? So which are one length far from that particular vertex.
One edge far.
One length far. So within one edge, I can travel to that particular vertex. Right? So A square will give us all the paths which are two length far. Like now in A square, here itself, let me compute this, let us take this as the A, and we will look at A square. So computing A square is like this. This is how the matrix multiplication works. So all the row elements, each of the row elements will be multiplied to the column elements, and all will get added. So simply that is the thing. So I will show you now. Now we are going to multiply these two things. And what will the A square represent also we will see here. So this is the A square. And this will be like, see the first entry. So whatever the first entry is there. So that will be product of this with this, this with this, this with this, and this with this, this with this. So you take the first row from the first vertex. So first row, you consider the first row, and you consider the first column in the second vertex. Okay. So by considering these two rows, now I have 0, 1, 0, 1, 0, and I have 0, 0, 1, 0, 1. So the first row, first column entry of the first matrix will be multiplied to the first row, first entry, and the first row, second entry will be multiplied with the first column, second entry. So first row, third entry will multiply to the first column, third entry. So like this. So this is how the multiplication will happen, and the corresponding values will be get added. So we are going to get 5 values. 0 multiplied by 0. So this is the product. And 0 multiplied by 0, we are going to get 0. And 1 multiplied by 0, we are going to get 0. And 0 multiplied by 1, we are going to get 0. And 1 multiplied by 0, going to get 0. 0 multiplied by 1, we are going to get 0. So if I add all the zeros, I will get 0 again. Okay. So that will be the entry for the first row, first column. So you product the first row and first column, and you will get the first row, first entry of the multiplied matrix. The same thing holds for rest of the things. So if I take the first row, second column, I will get the first row, second column entry. So first row, so you take the first row and you take the second column now. So second column is 1 0 0 1 1. So again you multiply this with this, this with this, this with this, this with this, and last one with the last one. So what will I get? 0 times 1 1 0, 1 times 0 0, 0 times 0 0, 1 times 1
We will
here
get
we are
1.
going to get 1, and 0 times 1 will be 0. So this will be 1. Like this I am going to fill.
But these are for undirected, no? A square.
See, right now I am computing it for directed, right? So this is a directed adjacency matrix. You can compute for directed also. Okay. So if I fill the whole table,
Method will not change. It is only
method
matrix
will not change. This is how you do the matrix multiplication.
Correct.
Sir, in
So,
short, we are.
the A square does not have one step path, means direct part will not be included in A square, right?
Right. So you'll only get the two length path.
Which is
Two
reachable,
length
sir.
paths.
So
Sir, in
if
short,
it
A
is
square
A to the
means.
power 4, A to the power 4, then it will have one and only 4 length path.
For this particular thing, is it?
Yes, sir. Yes, sir.
Okay. For this particular thing, maybe there is only one path, I guess. So
Sir, in
you
A
try to fill
square,
the table.
can we have in A square? Can we have entries other than zeros and ones?
See, if your sum is you are getting more than 1, then we will just simply give it as 1, because whatever the sum you are going to get, if you got 3, for suppose if you got 3, so that 3 represents you have 3 paths, 3 two-length paths that are going from that vertex to that vertex.
Okay.
Okay. If you got
So
the
when
entry
in the question paper you had asked for alpha and beta, no? So in that place, if we have a 2, when we multiply these two matrices, we get a 2. Like we have a 2 here also. In the second row, 5th column. Then alpha and beta, will it be? If that place, if there is a beta, then will it be considered as 1 or 2?
1.
Okay. Okay. Fine.
Okay.
Okay,
So this
thank you.
1, see, this 0 and 1s are just representing there is a path,
The edges,
there is no
connectivity.
Yeah, connectivity, reachability, basically.
Okay.
So there is a path, there is no path. So
Okay.
A represents, is there a path of length 1 to that from vertex U to vertex V? If yes, 1. If no, 0. And A square represents, is there a path of length 2 from vertex U to vertex V? If there is a path, if there is at least one path, then the entry will be 1. If there is no path of length 2, then the entry will be 0.
0.
And A cube will also the same thing. A cube will give me, if there is there a path from vertex U to vertex 3 of length 3 only.
Okay.
If yes, the entry will be 1. If no, the entry will be 0. So all the entries will be binary, either 0 or 1. Is
Or
there a
1.
path or no path?
Sir, if we
That's because it is adjacency matrix, correct? That's because it is adjacency matrix, this one. That's why we are only looking at 0 and 1, correct?
Its adjacency matrix is only for A. A is only called as adjacency matrix. Okay.
Can we do the graph if we do, just not by metrics, looking at a graph itself? So,
Looking at a graph, you wanted to compute A square.
So the graph, if I so my B will be 0 and C will be 1. Is that one?
What is B will be 0, C will be 1?
That the matrix.
B through Cth entry, is it?
Yeah.
Okay. B through Cth entry will be 0. You are saying?
Yeah. So it's like, okay, first row itself, no? So
yeah, looks like it is 0, but here there are only 5 vertices. Okay, you can say it directly. What if there are some 10 vertices and there are some 30-40 edges?
Okay.
Then it will be difficult to look for is there a path. So that is a time taking process, right? It's better you take the corresponding bth row and that particular uth row and vth column and multiply it and check whether it is giving you non-zero value or zero value. If it is giving zero value, then there is no path of length 2. If it is giving non-zero value, then there is a path of length 2.
Okay, thank you.
Okay. Yeah.
In A matrix, if there is an edge between suppose two vertex A to D, and in A square matrix, it is also there is an edge between A to D. So we can infer that we can reach at D by one step or by two step, like means say one level or two level edges we can reach, right?
Right.
Okay, nothing.
Right. Okay. So that is why. So everyone understood this how to multiply two matrices.
Yes, sir.
Yes. Okay. So once you multiply a square, see this A square matrix. A is the adjacency matrix. I already told this term. Adjacency refers to between two vertices. So it will give us whether the two vertices are adjacent or not. So that matrix will give us whether the two vertices have a common edge, sharing a common edge or not. Okay, that is why it is called adjacency matrix. And this matrix is also, you can say, it is gives me the paths of length 1. Okay. If is there paths of length 1, then the entry will be 1, or else it is 0. And A square is paths of length 2. Similarly, A cube, like this, A square, A cube, A to the power I will give me paths of length I. Okay. And you can make sure that if your graph have n vertices, then A to the power n is a zero matrix. Zero matrix means all entries will be 0.
So can you repeat, sir? What?
So if you have n vertices, then the maximum length of a path can be of n minus 1 length, right? But you don't require this, man, right now. We are going in depth discussing about adjacency matrix and how these are helpful, how A square, what is A cube.
A to the power
Sir,
n
we
minus 1 will
can
not
proceed
be
further,
0.
sir.
Yeah. So, okay, you don't need this at all. No need to worry about this. So just
We can
understand
proceed
this.
further.
Matrix multiplication, just understand matrix multiplication.
Okay.
And understand this, what this A to the power I represent. A to the power I matrix represents. Okay.
So here
actually,
A
it
to the
will
power
be
n minus 1 will not be 0 now, because maximum n we can't give by n minus we can go. Okay.
Yeah.
So, sir, like if we want to compute A4 matrix, it is necessary to compute A3 and then we can't go
No. You multiply A square to A square, right?
Oh, if we want 4, then A square to A square.
A square to A square, you will get A to the power 4.
Okay.
So it's like path of length 2. So you can understand it easily. This matrix is basically paths of length 2. And this matrix is also basically the paths of length 2. So if you multiply, you will get 2 plus 2, which is 4. So paths of length 4 you will directly get.
Okay. So similarly, for if we want 3, we can do A into A2.
A square into A also works, and A into A square also works. Okay.
Yeah.
So actually, sir, I had a request, sir. If you, in case you feel that some question is not important for the exam in terms of exam, you can tell, and we can move
Just now
forward.
I told, right? Those things are right now. See, learning concepts, I agree, but we are not. This is not the time to learn more concept.
Yes, sir. Yes, sir.
Let's skip, right?
So you can just, if somebody asks something, you can tell like that, and we can move forward.
Okay.
Thank you.
So
because we are just revising it.
So we are just revising the concept, basic concept. Don't worry about exam will be difficult. Exam is okay, decent. Okay, if you follow the basic things, you can come out with flying colors.
Okay.
So let us move forward and discuss vertex coloring quickly. So again, this vertex coloring is not a new thing to you all. It's just the find the minimum number of colors that are required to color all the vertices such that no two adjacent, so remember this, adjacent, so no two adjacent vertices have the same color. Okay, so no two vertices, so no two adjacent vertices, meaning, so if two vertices are having a common edge, then those two vertices are called adjacent vertices. So if there is a common edge between two vertices, that two vertices should not have the same color. So that is how you have to color the graph. Color the graph means you have to give one color to each of the vertex, and we want the minimum number of colors to be used. Okay, let me take an example. And also you have seen many real life examples in terms of vertex coloring. So one good example is partitioning into compartments. So if there are 10 chemicals, so let me take the example. So if there are some, okay, right now we will take some 7 chemicals, and few chemicals when came into contact, they will burst. Okay, so now you are the lab in charge, and you have to make sure that blast should not happen inside the lab. And now you have to request the authority to give you some warehouses. So you have to make sure that you ask the minimum number of warehouses. If you ask for 10 warehouses for 7 chemicals, if you ask 7 warehouses, authority will also remove you directly. So you are not being optimized. So you should be thinking optimal. Thinking optimal means you can keep few chemicals in one warehouse, where those two chemicals, even though if they come into contact, blast will not happen. So those things you can do, and you have to ask minimum so that authority can also provide you those number of warehouses. And you should have a solid proof saying that if you give me less than what I asked for, then definitely there will be a contact between two chemicals, and definitely there will be a blast. So this is how you have to argue. Okay, now there are seven chemicals. Let me take C1, C2, C5 this side, C3, C4, and C6, and C7 is here. Okay, and also they said we have the list of chemicals, inflammable chemicals, incompatible chemicals. So looking at that list, we can actually draw the graph. So how we draw the graph? By considering each chemical to a particular vertex, and how we draw the edge between two chemicals. So how should we define our edge?
C7 got repeated. Quick observation.
Hmm?
Quick observation. C7 got repeated.
C4 this
is. C7. Okay. Now it is correct. Thank you.
Okay. Yeah. So I repeat. So we are interested to. So there are few chemicals. When come into contact, they will blast. So when they come into contact, they will blast. So now your work is to separate those chemicals and keep it in different warehouses. So this is the thing, and you wanted to see this problem in graph theory, and you wanted to draw and look at in terms of graph. And you have taken 7 chemicals as 7 vertices. And now how should I define, or how should I add edges to this graph?
With those
last, if the two chemicals come together, then there's an edge.
Yeah. So if I will draw an edge between two chemicals, if those two chemicals come into contact, they will blast. So that is how I have to draw the edges. So let us say we have drawn it like this. Considering that in mind, we have drawn the edges like this. So C1 and C2 cannot come together. C1 and C4 cannot come together. C3, C7 cannot come together. These two cannot come together like this. So by looking at the list, you made these edges.
The edge means they are incompatible. If there is an edge.
Yeah, if there is an edge means, so if there is an edge between two vertices, mean
Blast.
Yeah, they are incompatible. Incompatible, or if they come together,
means that
they will blast. So incompatible means that if they come into contact, they will blast. Okay. So now once I represent this, so what we have to do? So what we have to do is, if there is an edge, that means they are incompatible. So those two cannot be kept in the warehouses. So C1 and C4 shouldn't be in the same warehouse. So they should be separately kept. So now you can see this. This is a graph coloring problem. And you can say that, so for one warehouse, I will give some color. So now my work is to find the minimum number of colors I should use in order to color this graph, and that minimum number of colors will serve my problem. So that will give me a solution. So minimum number of colors I get, so those many warehouses I require. So what will be the coloring? How should we start the coloring first of all?
So we see which one has maximum edges.
Okay, you can start it like that. So if you don't know anything, start with what the person has said.
C1.
Okay, so C1 or something else.
C3 also you can take, or C7.
Sir, if we take C1 as red, then we cannot take C2, C5, and C4 as red.
Okay,
color.
so let us take C1 as red. So now C5, C2, C4 cannot take red.
Yes.
But C3 can take red, C6 can take red, C7 can take red.
Yes.
So what you have to do is, you have to fill the first color to maximum number of vertices that are possible. Okay. If I give it to C3, then I cannot give it to C7, and I can give it to C6. But instead, if I have given it to C7, so just for explanation, so if I have given it for C7, then I cannot give the red color to C3 as well as C6. So I can give my first color to only two vertices. But look it in the other way. If I had given red to C3, then I can give red to C6 also. So three vertices got more number of colors. And 99% of the chances, even though you take C7 as red, it will not matter. So it will give you the same minimum coloring only. But there will be 1% of exceptional cases where this matters. So that is why before giving colors, just make sure you are giving the first color to the maximum number of vertices possible. Okay. So
basically the first color should cover maximum number of vertices, is it?
Maximum number, that will give you the best answer or the correct answer in 100% of the cases.
Okay.
Okay. And even though you don't follow this, 99.5% you will reach the correct answer only.
Okay.
Okay. Yeah. And in this particular graph theory, in our course, you will definitely reach 100% to the correct answer. Okay.
Actually, sir, there is a question in mock wherein actually the answer which I got was 4, but the correct answer given was 3.
Yeah, it's
I
me
didn't
too.
understand how it the latest mock.
So Varun also, actually,
Last one.
Mark 7, Mock 7, they have given exactly the same question. We all
Same
got
thing, and
4.
that there it was 4.
Then 4 was accepted, but here they said
Okay,
it is
okay.
3.
Okay, then maybe the answer given was wrong. So it is 4 only, I guess.
Okay.
Okay.
Yeah. So once you fill the first color, then you no longer can give C4 to red, C2, C7, C5. So then now you have to pick the second color. So after picking the second color, you just give whatever. So for C2, you can give C2. Once if I give to C2, I cannot give it to C5, C7. So I have to give it to C4. And I am done. I have to choose the third color now. So the third color, I can give it to C5 as well as C7. Okay. So the minimum number of colors required to color this particular graph is 3. Right? 3 colors required. Or the vertex coloring is 3. 3 colors required. Which implies 3 warehouses are required. Now you can argue with your authority, right? If they say that finish within 2 warehouses, now you can show this graph to them and say, if I have only 2 warehouses, my C5 and C6, if I cannot keep my C5 and C6 in both the warehouses, so definitely if I have kept in any one of the warehouse, blast will happen. So you can convince the authority and you can get the third warehouse also, in which you can keep C5 and C6, C7 chemicals.
Sir,
So this is
sir,
where,
would you repeat the condition? I mean, trick to get 90 some percent. What you said?
so
The
what I
trick.
said is you try to give the first color to the maximum number of vertices possible.
Okay.
Okay. Yeah. So like that you can get the coloring, minimum coloring.
Sir, mock solution is not released yet.
Yeah, mock solution, I don't know why they didn't release, or okay, I will discuss few concepts on that. Sorry, questions which are very difficult in the mock. Okay, let me complete this.
Sir,
Okay, so that is vertex coloring. Yeah.
Sir, will the end term paper will be more difficult than this mock, or how will it be?
See, it will be of same level. It might be easier also for few of them. It might be difficult for few of you. Okay, it depends on how you prepare. So on which
Because quiz
topics
2
you
was
more focused.
difficult. Quiz 2 was difficult compared to quiz 1. So that's what I wanted to know, whether quiz 3 will be much more difficult.
No, not like that. See, 50, not even 50, 60% of the questions which you are going to see in the end term, you might have seen it somewhere in the activity or practice or any mocks or somewhere. So maybe some 4 or 5 questions might look new, but the concept is same.
Same.
So if you understand the concept, you can also do those. Okay. And there will be 1 or 2 tricky questions in every QP. So if you are stuck with that tricky question, the time will run out. So if you got the trick, just answer it, or else just move on and look for the easy questions in the QP.
Okay.
Okay.
Okay, sir. Thank you.
Yeah. So let's, yeah, we are running very late. So let us cover vertex cover now. So what is this vertex cover is basically, so vertex cover, I have to find a minimum. So minimum vertex cover. So what is this minimum vertex cover is basically, we have to find a minimum subset of the vertex set. So let's say, so the subset is like VC. Okay, I have to find a subset, and that to be minimum. It should be minimum. What subset? Subset of the vertex set. So if I have some 10 vertices, out of those 10 vertices, I should pick some subset. So I should pick some 5 or 4 or 6. So how should I pick is like such that all the edges are covered. So what do we mean by covered? Covered means this. So in my, so if there is an edge from A to B, so AB there is an edge in your graph. If A to B is an edge, then either vertex A or B should be in VC. Okay, for all such edges, for all edges. Okay, this will hold for all edges, not only AB. So if there is an edge between two
Both A
vertices,
and B.
Sometimes it can both A and B also can be there. It is either or. Okay, it's like A union B. So it will include both, only A, only B. Okay, either A or B should be there for every edge, for all edges. So then we say all the edges are covered. Okay, so basically our idea is
So
we have
this
to
is
pick
minimal or minimum?
minimum for
So
vertex
this
cover.
this is that example of
Minimum.
CCTV camera. No? Okay.
Okay. So what I have to do is, if a graph is given to me like this,
Please, can you go up a minute? I was writing it down.
Okay.
So does it minimum vertex covers? Does it have two different cases for directed and indirect graphs?
See these things, vertex coloring or minimum vertex cover or maximum independent set or matching. So all these things will be dealt on only undirected graphs. Okay. Undirected graphs. Okay.
Thank you, sir.
So in our course, so we are only looking at undirected graphs.
Thank you, sir. I noted it.
Okay. Yeah.
Okay.
Okay. So A, B, C. Okay, like this. So if a graph is given to us like this, now count the number of edges first. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 edges need to be covered. So you understood the definition of covered, right? Covered meaning. So
9.
not, huh?
9.
So this edge is covered means either A or B should be in my VC. Right? Like this, I have to cover all the 10 edges. Right? So let us slowly build our VC by covering few edges. So how do you start? So for this also, pick
maximum number of edges.
Maximum number of edges that are incident to that
Connected to
particular
vertex.
vertex. Okay. Now E looks like having the maximum number of edges. Right? So 4 edges are incident to E. So let's pick E in our vertex cover. So if I had picked E in our vertex cover, now this edge is covered, this edge is covered, this edge is covered, and this edge is covered. So I have covered 4 edges. Still 6 edges are pending. Okay. Next, what you have to do is, in order to pick the second vertex, so you remove whatever are covered, you don't consider it now. So now pick the vertex which covers the maximum number of uncovered edges now.
A.
A.
So A has some 3 uncovered edges. C also have some 3 uncovered edges. That's it. Pick either A or C. It's fine. Okay.
C.
So let's pick C. Okay, let's pick C in one case, and let me write A in another case. Okay. Just I am writing, but I am following this only. Okay, let me, the red thing I have picked C now. So E and C we have picked, and these edges are covered, right? So how many edges are covered now? 7 edges are covered, and still 3 edges need to be covered. And now just follow the same trend. So pick the vertex which is incident to maximum number of uncovered edges.
A.
A. Now I have to pick A. So in that case, it will be C. So in this case, it will be C here. Here it is A. Okay. Now I have picked A also. And this is covered. And this is also covered. And finally, I have to cover one more edge. So I can pick D or F. It's up to us. So you can pick D or F. So D. So you see minimum number of vertices that are required to cover all the edges is 4. So this
So
will be the
cardinality of VC will always be same.
VC will always be same. Minimum vertex cover will always be same. Minimum VC. Okay. So why we are looking at minimum is because that is the optimal case. So optimization of vertex cover will happen by looking at the minimum. So by taking minimum number of vertices, can I cover maximum number of edges or all the edges? So that will be the optimal process. And I can.
What does 4 represent?
4 represents
minimum
the vertex
vertex
cover
cover.
cardinality.
Minimum
vertex cover.
Cardinality of minimum vertex cover.
And
so I
so
can
vertex number is the same.
What if?
Vertex number.
There is no vertex number.
There is terminology vertex number.
Vertex number actually refers to degree, I guess.
That means that is not this 4, no?
That is not this 4. See, vertex number, I don't think it will come in vertex cover. Vertex number, even I haven't seen the terminology. Maybe it refers to vertex number, refers to a degree of that particular vertex in an undirected case. Maybe. That also I'm not sure.
DFS search. We assign number to vertex for traceability.
That is DFS number.
So vertex number, can you recheck it? Even I will check what is this vertex number. But right
Actually,
now,
I have studied graph theory somewhere that vertex number, covering number, there is some terminology like that.
Covering number. No. So even I did 2 courses of graph theory, but I nowhere come
Sir, but
across this.
we can say no, sir. It's
Maybe. Okay. Anyway, not required now.
Sir, in here you wrote 3 vertex cover, right? The first one is considered as minimum vertex cover, sir.
Yeah, first one is the minimum vertex cover. Again, here also this is also minimum vertex
Only
cover.
first one, sir.
Yeah, this is minimum vertex cover. Let me write the second one. I can actually take A, B, C, D, E, F, G, all the vertices into my vertex cover. Okay, no issues, but this will not be the minimum. So if I take all the vertices, that will cover all the edges. So it satisfies the property of vertex cover, but it will not be the minimum vertex cover.
Okay,
so
sir,
we are
thank you.
interested to find the minimum vertex cover. So this will be the minimum vertex cover, and this also will be the minimum vertex cover. So your minimum vertex cover may not be unique, but the cardinality of minimum vertex cover is unique. So it will have the same number.
Okay, sir.
Okay. So if it is 4, it will be 4. Okay.
And sir, what is just vertex cover?
See, vertex cover is like just now we saw, right? You have to cover all the edges. So you have to pick a subset of vertex set where that vertices will cover all the edges.
And sir, minimum must have the lowest cardinality. Not we
Lowest
cannot have.
cardinality. Yeah. Lowest cardinality. So with
So,
ECAD, I can cover all the edges. So you no need to
so
have all the vertices to cover all the edges. It is enough to have only 4 vertices. So that is what this
all
is.
vertex. So all vertex cover are not minimum, right, sir?
All vertex cover are not minimum.
If it
Or
is
not
optimized,
minimum
then it
vertex
has
cover.
to be minimum.
Okay. Shall we move?
Yes, sir.
Yes, sir.
So that is about vertex cover. And let us discuss.
Next one.
Yeah, matching. So right now we have seen in regards of vertices. So we have picked subset of vertex or we have colored vertices. So in matching, what happens is we have to find a minimal. So we don't even right now we don't even require minimal these things also. You have to find the minimum subset of the edge set. Okay. Now it's not vertex set, it's the edge set. So what you have to do, you have to see the number of edges, what are the edges are there in your graph, and you have to pick a minimum subset of that edge set. So how should I pick? So let's say it is M, that subset is M. How should I pick such that?
Sir, MCE what?
M, it's subset symbol. Okay. So such that, so I said M is the subset which we are going to find, M, minimum subset. So which is subset of E, which is edge set. So such that no two edges in M share a
Same vertex.
common vertex. Okay. So understood? Such that no two edges in whatever the subset I am going to pick that share a common vertex. So let us take an example. So sharing a common vertex means like this. So if it is like this, so this edge and this edge shares a common vertex B. So that means these two at a same time are not allowed into my set M. So if I had picked this in my M, I cannot pick this. Okay. So it's not minimum. I think it's maximum subset. Maximum and maximal, right? Am I right?
So maximum
Yeah.
set, we are calling it as perfect matching.
No, you have to find a subset of edge set E such that no two edges in M share a common vertex. And you have to have the maximum subset.
Okay, so
They
you
will
mean to
say
say we need to include maximum number of edges into our subset what we are collecting.
yeah. Maximum number of edges we have to include.
Sir, I have one more question in this context. What does this signify actually? In the tree and in the whatever graph or tree, whatever you have drawn, we can take only one edge at a time, right? Either AB we can take or BC we can take. What does this signify? Does this have any practical question as we
Of
discussed
course,
in
of course,
Vertex?
of course. See, I will take an example of a practical application also. So we will take an
Yes, sir,
example and
please.
see. Okay, yeah. So why we are looking at maximum and why not? Why this will be the optimal case? Okay, let's suppose say there is a school, and in the school there are some 5 classrooms and some 4 teachers. Okay, it's not okay. 4 classrooms and 5 teachers, and we know that few teachers can teach more than one subject, and each classroom should be occupied by only one teacher at a time. So if classroom 1 has teacher 1, then in classroom 1 teacher 2 cannot go, teacher 3 or teacher 5 cannot go. It's like one-to-one mapping between classroom and teacher. Okay, and any teacher can go into any classrooms, or there might be some restrictions that few teachers can only teach classroom 1 and classroom 2. Few teachers can teach classroom 3 and 4. So like this, if there is a system like this, okay, now how we will convert this problem into graph is we will consider all the classrooms and teachers as the vertices. So classroom 1, classroom 2, classroom 3, classroom 4, teacher 1, teacher 2, teacher 5. Okay, so now we will draw an edge between a classroom and a teacher vertex if that teacher can go and take a class in that particular classroom, and we know the list of teachers who can go into their corresponding classrooms. Okay, so now this is how it is maybe. So teacher 1 can go to classroom 1 and classroom 3 for teaching. Similarly, teacher 2 can go to classroom 1, classroom 2 and classroom 4. And like this, teacher 3 can go to classroom 3 and classroom 4. Teacher 4 to 2 to 1 to 4. And teacher 5 only to 3 and 4. Okay, so by looking at the schedules and teachers, you have drawn this particular graph, and this graph represents which teacher can go into what classroom. And now you have to schedule. Okay, you have to schedule now the classes. So for the first period, how will you schedule? So which teacher should go to which classroom? So how will you schedule actually? Right, 2 teachers cannot go into one classroom, that is for sure. And at a time, teacher 1 cannot go into 2 classrooms. So what we do is we do the matching between classroom and teacher. So we'll try to find the matching.
So each pair should be different, right?
Yeah. So it's like pairwise matching. So vertex will. So if teacher 1, if you are scheduling for the first period, teacher 1 is occupying classroom 1 and teaching. So now C1 classroom 1 is occupied by teacher 1. So into the classroom 1, no teacher can come in, and teacher 1 cannot go into any other classrooms. So if you add this edge to your matching set, then the edges which are connected to this, so edges which
This
are
vertex
connected to it,
Connected to C1.
or adjacent, connected to a same vertex. So vertex C1 and T1 are now blocked. So all other edges which are coming to C1 and T1, you cannot pick into the matching. So this is a one practical example. So you will try to come up with a matching. So this is a matching. So this and this.
Basically, it is used to prepare a timetable, is it?
Yeah. So this is this and this, and this is this is the matching. So there are 4 classrooms. So you can only assign 4 teachers, and teacher 4 will be left alone. So he will not take the first class. Okay, so like this, you will, so out of, so here we have only 4 classrooms and 5 teachers. Suppose you consider right now online teaching has been tremendously increasing. So if there are some 100 events happening at the same time, and there are some 110 people who can take not all the, some of the 100 classes. So how will you schedule? So for that, this particular matching will help you. It's like one-to-one mapping. Okay. So yeah,
Okay,
here
sir.
in this particular
This
example,
was clear. Okay,
yeah,
sir. This was clear.
yeah, in this particular example, we will try to find the matching, and this is like we are going to get the maximum matching. So maximum number of edges, 4 edges, which are not adjacent to each other. Okay, this C1 T1 edge, C2 T2 edge, and C3 T3, and C4 T5. So no two edges share a common vertex. So you can check. So this will be a matching, maximum matching. Okay, so this is how you have to come up with the matchings, and also you can find the number of matchings in this particular thing. So you can actually find the number of different possible matchings. Yes or no? So why only C1 T1 can take? Why only classroom 1 can be taken by T1? So C1 can be taken by
T2
T2.
also.
Yeah, T2 also. And then T1 can take C3 and T5 can take C4, like this. Right? So you can also compute. So here the graph is little complicated. If the graph is easy, you can also compute the number of different types of matchings. So give it a try. Take this example itself, draw it neatly, and try to find the number of different matchings possible. Okay.
Sir, what kind of question will be asked based on this concept?
So right now, whatever I discussed.
Maximum matching or different kinds of matching will be asked?
See, whatever I say, how can I say the direct question? See, I will give you some 3,
I'm
4.
just asking.
See,
Because
you can
in the
get
mock,
any kind of question.
okay.
Okay. So whatever I discussed today, so treat this as a high priority thing. So,
Can you scroll
so I
down
have
the
given.
page? Can you scroll down?
So I have given you something to look into. So look into vertex coloring, vertex cover, and matching. So within these 3, you can assume that there might be one question on these concepts.
Okay.
Okay.
Excuse me, sir.
Like
Can you
this.
please take a mock test question?
Yes, sir.
The
Matching
question 6
questions.
and question 8.
Okay, let's take the mock test question then.
The matching is same as maximum.
Dags topic is left.
DAG topics are left, I know. I will cover. So I already said we are running late. Okay, let me complete this.
Complete topic.
Let us complete topics first, is it?
Yes, sir. First complete.
Yes, sir.
Okay.
Complete topic first.
Let us complete
Later,
topics. Okay.
and then do
Later
the
we can
doubts
do.
and
Yeah.
questions. Yeah.
Sure. So that is about matching. So you have to look for the maximal matching set. Also try getting how many different types of matchings you can get from a particular graph. Okay. So now let's move
Sir, am
ahead
I
and
audible?
yeah.
Hello.
Sir,
is matching the same as maximum independent set? Like that was there in a
No.
different.
No, it's different. So maximum independent set is finding the maximum subset of vertex set. So there we are going to find the subset of a vertex set. Here it is subset of an edge set. Okay, completely different. Okay, you just go back and look into it. So now let us see BFS and DFS. And that too, I will give you the original graph first and we will draw the BFS tree. And from BFS tree, we will try to predict
graph. Yes.
how we can draw the graph. So quickly, let me take the previous example. So this example. So let me do it. Okay, so let us draw the BFS tree for this particular graph. And you know, BFS tree will vary with the starting vertex you pick. So if you pick vertex A as the starting point, you might get some different tree. And if you pick E as your starting point, you might get another tree. So BFS tree is dependent on the vertex, the starting vertex. So let us pick the starting vertex to be A.
Sir,
And
also it depends on how Q is
how we are exploring.
Yes, sir.
So let us pick
Q order
alphabetical order. Yeah. So we are mentioning that you have to explore the vertices in alphabetical order. Okay, and starting with A. So how do I draw the BFS tree? So BFS tree is basically the level by level search. So once if I start from vertex A, that will be denoted as level 0. And from vertex A, I will explore all the neighboring vertices in alphabetical order. So if I look at the neighbors of A, so the neighbor or adjacent vertices, a neighbor of A are B, C, and G. So B, C, G will come in the level 1. So this will be the level 1 vertices. And after B, C, G, we will visit vertex B. And
E also.
Sir, E also.
Yeah. E also. B, C, E, G. B, C, E, G will come in the level 1. And we will visit once after exploring all the neighbors of A, we will move to one of the neighbor. We will visit one of the neighbors. And we will, as it is mentioned that alphabetical order you have to move. So we'll go to B and look for unexplored vertices. So once if I from A, now I have visited B. Now I am at B and I will look out for unexplored neighbors. Are there any unexplored neighbors? So let us say this A is visited and explored. So now if you are at B, if you see there are no unexplored neighbors. So what I will do, I will just come back to A and I will just go to C. Next vertex. Once if I reach C, yes, now I am at C now. So if I see, are there any unexplored neighbors of C? Yes, there is an unexplored neighbor of C, which is D. So D, we will have an edge and we will draw D in the level 2. So now what I will do is, there are no unexplored, only D is the unexplored vertex and I have added it to the vertex BFS tree. I will go back to A and I will move to E. So alphabetical order, C after E. So now I am at E now. I visited E and I will look out for are there any unexplored neighbors. So F is an unexplored neighbor. So I will draw an edge like this and F will also come in the level 2. And F is
But
another
to D.
I'm sorry. So once
Sir,
you
when
get
we went to D, there was a F was the unexplored neighbor.
See, we are not going to D. We just explored to D. Visiting D and exploring D, both are different.
Actually, it is not different. We have a queue of E and G.
I'm not getting.
Actually, sir, we are not doing DFS. So we have
Yeah,
to
yeah.
explore E and G before exploring level 2.
Yeah, correct. So we have to explore level by level. So once after exploring A, which is in the level 0, I have to explore B, C, E, G, which are in the level 1. And I will visit these vertices first, and then later I will go to next level vertices. So like this, level by level, it explores the graph level by level. Okay. And now this is the BFS tree we got. So this will be the BFS tree. So when do you stop looking into again going and exploring like this? When do you stop drawing the BFS tree? When you get all the vertices in your graph undirected. I'm talking about the undirected case. When you got all the vertices in your BFS tree, then you can stop. Yeah. Then you can stop drawing the BFS tree, and that will be your BFS tree. So now this is the BFS tree we got from the graph. So how do we predict the original graph? Yeah.
In this one, you have a vertex from B, an edge from B to E. So why? Okay, fine. E is already in the level 1. Sorry. Thank you.
Okay. Yeah.
Sir, I think we could go up to maximum one level up. Sorry, means we could have a edge one level up at max.
One level above or one level below or the same level. So y is important. So why only we can have one level above or one level below, that we will see. So this is the BFS tree you have, or I will just change it. Okay. Okay. So if your BFS tree is like this, so just draw how many number of levels are there. So level 0, 1, 2, and 3. So now this is a BFS tree, right? And it actually explored. BFS tree means, so this particular diagram which you are seeing is actually explored level by level. So all the vertices you see in level 0 is a starting vertex, and all the vertices which you are seeing in level 1 are adjacent to the vertex above. So observe this thing. So which are all the vertices will come in the level 1. So while you draw BFS tree, which all vertices came in the level 1? B, C, E, G. What are these vertices B, C, E, G?
Which are adjacent to
Adjacent to A.
Adjacent to A. Adjacent to A. Okay, remember this. So by looking at this BFS tree, what you can say, B, C, E, G are adjacent to A. And also you can say D and F are not adjacent to A. Yes or no?
Yes.
Yes.
Right? So you can also say this, if D and F are coming in level 2, then definitely there is no direct edge connecting A and D, A and F. If there is a direct edge, what would have happened?
It would have come in level 1.
It would have come in the level 1, correct. So now you can see here. So now what can we draw? So we can actually predict like, okay, there is a vertex A and the adjacent vertices are B, C, and E. And now within this 4, we will look at within this 4, we will look at a few things. What if there is an edge between EB? Will my BFS tree change, or will I get the same BFS tree till here?
Same.
Same, right? So even though I have an edge between E and B, it will not change my level 0 and level 1 vertices. So that means I can, okay, I just wanted to change the color. Yeah. So that means B and E can have a direct edge, can have or cannot have. Okay. So we are not saying that it must have, it can have. Right? What happens if there is an edge between E and C?
No issue.
Is
It's
there
a cross edge.
is there an issue or no issues? Even if I
nothing,
draw
sir.
BFS tree for this graph,
No issue, no issue.
this will work. The same goes with CB.
Yes.
It
can.
We are exploring
It
only
can.
A, so these will not affect.
Right. So same level vertices. So this is of level 1 vertices, right? So all BCERs at level 1. So even though I have an edge between BCE or CE or BE, it will not affect my level 0 and level 1 of the BFS tree. Right? Till here it is clear.
Yes, sir. But if someone asks how many label are there, so we will say 3 level are there or 4 level.
So it's like 4 levels, right? Number
4
of levels. If we ask the number of levels, it's 4.
Starting from 1.
Starting from 0, no?
Starting from 0.
0, 1, 2, 3. Okay, we won't ask it. Okay. Don't waste time. There is nothing like number of levels or we are not focusing on number of levels.
I was counting like floor by floor, 1, 0 to 1, 1 to 2 to 3 floor.
Okay, so let's move and see. Let's go one more level. So let's come now. Our bar is set to level 2. So here, till here we are looking. Okay, so now D is also there, and there is an edge from C to D. Okay, now see, can I have an edge between E and D?
No.
No, sir.
No.
Yes.
No.
You can have, sir.
You can
Yes,
have,
sir.
We
Yes,
can
sir.
have.
Level we can have. Cross
We can
branches.
have.
Edges.
So why we can have?
But we have explored C. So
For Vertex
adjacent level, we
also
can have close edges.
BC or in the same.
Only one level difference.
So see, alphabetical order. We are following an alphabetical order. So once if I start from A, so I will keep in level 1 vertex B, vertex C, and vertex E. Right? After that, so just draw the BFS tree of this particular graph. So I will go to B. So there are no unexplored vertices. So I will come back to A and go to C. Explore C. And while I explore C, I have an unexplored vertex D. So below C, there will be a vertex D, and this is how the BFS tree will look. The same BFS tree you are going to get, even though I have an edge between E and D. Now tell me, can I have an edge between B and D?
Yes.
Yes.
Yes, sir.
We can have.
Yes.
If you are going
So
at
you can
alphabetical
have-
order, not possible.
Right.
No.
So I said it's an alphabetical order now.
Yes. If it is in the B, that we have first.
So if there is an edge between, B and D, what would have happened? So instead of here, I would have explored D here itself.
So B is possible, but D and E is not possible because E is at a higher level.
E is possible, right?
B and D is possible.
If B and D is okay, so let's say if B and D is possible. So forget about this BFS tree. So try to draw the BFS tree of this. So we'll start with A. Then we will explore in alphabetical order A, B, A, C, A, E. Correct? Next, I have to go to B, right? Alphabetical order.
Yes.
And what happens when I go to B? If there is an edge between B and D,
yes, B and
I would have explored D here, right? But is this the same BFS tree which is given?
Yes, sir. No.
Are these two same?
No, because we have taken an edge between C and D.
Yeah. So that means if you had taken an edge between BD in your original graph, then the BFS tree will not look like this. It will look somewhat like this.
Tree
right?
structure will change, but the levels of vertices will will be same.
Sir,
Right,
what
sir?
I'm
All of vertices will be
Graph
same. Okay,
above,
fine.
the first graph shows that we have taken C over B for going to D.
Yeah. See, I already said it's an alphabetical order.
So first we'll have to take B only.
Okay. So if alphabetical is order is not given, whatever you are saying is true. You can also have an edge between BD. But as I said,
my
The
question is, sir,
alphabetical order has been given. Then we have to take the B and D.
That is what, right? That is why
not
there.
C and D.
That is why there will not be an edge between BD. This edge is not possible. If there is no edge, then definitely this D will come below C. Right? So
sir,
BD.
Sir, is this correct?
So if this alphabetical order is not specified, in that case we can take A to C and C to D. But if alphabetical order has been asked, then we have to go from A to B and B to D, isn't it?
No. Reverse,
See, here we are
reverse.
predicting the original graph. Okay, we didn't give you the original graph.
Sir,
But
when alphabetical order is given, only across the same level we can have edges, but across at the above level and below level will not be possible at all if we stick to the alphabetical order, right?
Why? D and E can have the edge, right?
D and E can have an edge. Okay,
sir,
so
I am asking,
whenever there is a vertex in this position, so it cannot have a link with the previous ones.
Like this, backward.
Okay. Backwards it cannot have, but future, I mean onwards it can have.
Okay. I will simplify this. Okay, I unnecessarily mentioned alphabetical order. Let's remove alphabetical order. Okay.
Because
So
when
this
we
is
are
going.
predicting what can be in original graph, we are only checking it can be either B and D is also possible, E and D is also possible. That level thing.
Okay, let's do it in your way only. Okay, better not to confuse. Okay, let us do it on our way. So can B and D can have now an edge?
Yes.
Yes, we can have.
Yes,
right? So one possible, see now one possible BFS tree will be like this. So I explore A. I start from A.
Sir, if there is alphabetical order is mentioned, then we cannot have edges between B and D, right?
Right.
Yes.
Right.
Okay.
And sir,
So, right.
what I am asking, if in question it is given that we have to predict the graph, but it is nowhere mentioned alphabetical or any other thing,
Then
we will
this
say
is
okay,
how
B
it
and
is.
D. Okay.
Then B and D can also have an edge.
Thank you.
Okay. Yeah.
But same level edges are possible. BC, CE are possible whether we consider alphabetical order or not also, right?
Right. So
BC,
forget
CE.
about alphabetical order. Okay.
Sir,
Right now,
sir, I have
forget
doubt.
about alphabetical order. Yeah.
Yeah, even though if it is not alphabetical order, looking for the BFS tree, if D is not would have, then it should be connected with B or not first. A, B, D. As we keep on exploring, first we explore A, then we explore B.
See, it's not like that. If it is alphabetical order, then this order also matters. This B, C, E order also matters. It is not alphabetical order, it doesn't matter.
Alphabetical order is given, then B will have to be connected to D, no, not C to D, no?
Depends upon tree, ma'am.
No, if there is an edge between B and D also, then
See,
in
you
that
are changing the question. You shouldn't change the question, okay?
have to be connected to D.
See, let me complete. You shouldn't change the question. In question, it is given that BFS tree is like this, okay? If it is like this, so what can be the original graph?
Sure.
So you are not supposed to pick the graph and come back to BFS tree.
Okay.
Yeah.
Just a prediction.
This is just the prediction. Again, this is just the prediction. It is not even the original graph. You are just predicting the original graph by removing what all edges are not possible. So what not possible is this edge. Definitely this edge is not possible. Even I consider alphabetical order or not alphabetical order. A and D. If there is an edge between A and D in your original graph, can my BFS tree be like this?
No, D will
No,
go
sir.
same level tree.
D will come to level 1.
And D will be in the level
D
1.
will be in the level 1. That means
Yes.
I am pretty much sure that there is no direct edge that is connecting A and D. Right?
Yes, sir. It's clear, sir. Yes.
This is for sure, right? Like
Yes,
this
sir.
we will develop.
Yes.
Like this we will develop. Next we will move to the next level, final
Yes, sir.
level. So final level we will go and add F and G also. And now if you observe, F and G are coming in the level 3.
Yes.
Okay. So what can be the case? If can E and F can have an edge between them?
No,
Is this
sir.
a possible edge?
No, no.
No.
Why it is not possible?
Because
Then
the
it will come to level 2.
difference is 2.
Then it will come to level 2. Correct. So that is why this is not a possible edge. This is not possible. Can F can have edge with C?
Yes.
No.
Backward, forward, something.
No, sir.
This one, C.
No.
No. Even if you have an edge between C and F, then also F would have come in the level 2.
Yes.
Right? So like this, even C and G also cannot have an edge.
No.
These red edges are not possible edges. Can A have a direct connection with F?
No.
Not at all. Right? A cannot have a direct edge with G also.
Yes.
Right? Similarly, G cannot have a direct edge with B.
If not have
G cannot have a direct edge with F cannot have a direct edge with B. Right? So if it has happened, if any one of these red edges are there in the original graph, then this will not be the BFS tree. Given BFS tree doesn't represent that particular original graph. Okay, you can exclude that. So out of the options, so if a question is given like this, so what you have to do is you have to eliminate the options. So out of the given 4 options, you have to eliminate the options by finding if there is if one of the option is like A and G is having an edge, then definitely that particular graph cannot represent this particular BFS tree. Okay. And whatever the red edges I have drawn is between more than one level different edges, vertices. So you see I have drawn.
Excuse me, sir.
Yeah.
Sir, how we connect the B to D? Can you explain?
How we connect is because see, even though if there is an edge, so I will do like this. Okay. So A, I have explored C, then B, then E. Okay, in order. And then in C, I have explored D. Okay, it can happen, right? I can explore D.
Yeah.
So then after that, I can explore F and G. So like this.
D can have an edge between B and D.
So B can have an edge between, yeah. Even though if right now I have drawn the BFS tree of this particular graph. So remove all the red lines, red edges, and whatever the remainder has drawn the BFS tree of it. So this is one possible
So
BFS tree.
we can pretty much stick to our earlier concept of one level below and one level above.
Yeah, one level. Yeah, correct. So that is what I am going to conclude. So BFS
because
tree.
there was a small point that you introduced, like when you put alphabetical order, BD is not allowed. So
Okay,
do we need to get that also into
No.
high importance?
No, not for this exam because I already prepared the QP. But maybe in the next term final exam, I might bring this concept into the picture. Okay.
Yes, sir. Time is limited, sir. Many topics.
So this is how you can predict. So for a BFS tree is given, what you have to look for is in your original graph, vertices which are on the same level or one level above or one level below or one level below can have an edge in the original graph. Okay, and you have to answer by eliminating the options. So you have to eliminate the options, given option. Okay, and that is, and DFS tree, it's like branch. So consider the branches. So I will quickly finish, and I just wanted to go to Dags as quickly as possible. So okay, if your DFS tree is given like this, and you have to predict the original graph, then draw on this graph only. So possible graphs are, first find how many branches are there. So the branches are this. So this is one branch. This is another branch. And this is another branch. And this is another branch. So there are 4 branches in your DFS tree. And for predicting the original graph, this is how you have to, these 2 points you have to remember. Same branch vertices can have an edge. Okay, same branch vertices can have an edge, and so no 2 vertices of different branches cannot, no 2 vertices of different branches can have an edge in the original graph. So that means these edges are not possible. B2E, C2E, C2F, C2I, E2H, E2F, so like this, D2H. So like this, if I pick 2 vertices which are from different branches. So here C and I are in 2 different branches. C is in the blue branch and I is in the gray branch. So in your original graph, C and I cannot have a direct edge. Cannot have. If it has a direct edge, then that means I would have come in the same branch itself. So this is DFS. This is depth first search. So I will explore to the depth. Like I will start from A, the next neighbor B, the unexplored neighbor of B, I will go to C. And if C is neighbor to I would have explored I also in the same branch. But because I is not in the same branch, it is in the different branch, then definitely I is nowhere connected to C. No direct edge between C and I. So that you can predict. That is how you can predict. So same branch vertices can have an edge. So within the same branch, so these are possible edges. C can have an edge with A, E can have an edge with A, F can also have an edge with A, and similarly I can have an edge with G.
So non-tree
So
edges. Non-tree edges, right? This is what I'm getting confused. Non-tree edges, something is there.
Yeah, see, these black edges are tree edges. So these blue edges are non-tree edges. That's it.
Right. Okay.
Okay.
Blue
so
edges
this is how
are
you.
What?
What?
Blue edges
This
are
is what I was getting confused in BFS.
Okay, don't worry too much about these things. Okay.
Branches, not edges.
These are just the branches.
Sir, in one line, all edge possible except branch edge.
Except different branches.
Yes, sir. Except different branches.
Different branches. Okay, so write this down. So same branch vertices can have an edge, but no two vertices of different branches like Ci or Ei like this. So C, E and I are from different branches. So E belongs to that red branch, this red branch, and I belongs to this gray branch. So they are from different branches. So E and I cannot have a direct edge. So that you can assure. Okay.
And sir, that bigger to smaller concept, forward edge, back edge, that is important or not?
That you just go through that things. Okay. Forward, backward.
That numbering based.
Number of forward edges, number of backward edges. You just go through it.
3.
Yeah. So Dags, let's come to Dags. Okay. I just wanted to discuss more emphasis on Dags and spanning trees. So
Yes,
if I
yes.
complete this Dags and spanning trees, I am okay. You can ask me any questions later.
But
Okay.
Dijkstra algorithm is also.
Yeah, Dijkstra also I will discuss, but I don't think Dijkstra requires so much of explanation. And
Please
why I
test.
am saying DAG is because just to give you that longest path, how you compute that longest path.
Topological sorting will be covered here. No?
Also, I'll cover topology also. So directed acyclic graph is basically the graph must be directed. So it should be directed graph, and also the graph should not contain any cycles. So no cycles in the graph. Cycles meaning if I start from a vertex and if I travel along edges and vertices, and if I can come back to that particular vertex again, then that will be a cycle and that path will be a cycle. So like this. So now you see if I start from A, I can go to B, B to C, and I can come back to A. So A, B, C, A. So this particular path is a cycle. So this should not be there in our DAGs, in our graphs. So cycles are not allowed. So if there is a cycle, it is not DAG. So without the cycles and also the graph is directed, then we say those particular graphs comes into the class DAGs. And these DAGs will have few properties. Each and every DAG will have a vertex with in degree 0. Similarly, there will be a vertex with out degree 0.
Sir, where in degree and out degree 0?
In a particular DAG. So facts of DAGs. So if you have a DAG with you, directed acyclic graph with you, in that particular graph, there will be a vertex with in degree 0 and a vertex with out degree 0. Okay. So let us take an example. I will give you two graphs now. So tell me which one is DAG and which is not. Which one is
second
DAG?
one is
Second one is clarity acyclic graph. Second one is DAG. Second one is
Second one.
Second one is DAG.
Second one is DAG.
So second one is the DAG because it doesn't contain any cycles. Why this is not DAG?
because no vertex has individual
Cycle is there. There is cycle AEB. Like
There is a cycle A.
BCD.
Correct. BCD is the cycle. So this is a cycle and this is not a DAG. And one more way of checking a DAG or not is you just look for the in-degrees of all the vertices. So if you don't have any vertex which has in-degree 0, then that is not DAG. Then definitely there is a cycle inside it. So you just find the cycle and say that it is not a DAG. So this is not a DAG.
So these are not the sufficient condition.
Which one?
Means if in degree
This
and
is
out degree are
sufficient.
0.
This is sufficient.
No, I am saying if in degree and out degree is 0, then that graph must be a DAG.
Okay. That is not the sufficient condition. If it is a DAG, then it will have these properties.
Okay, means these are necessary condition, but these are not sufficient so that we could say that they are DAG.
Yeah. Correct. Okay. So this is DAG. So you can check. So let us find the in degrees and out degrees. So what is the in degree of A?
0.
0, 0.
B?
2.
So correct me if I'm going wrong. Okay, I will just quickly write. So C?
3.
3.
Oh, sorry, 3.
D?
3.
E?
0.
0.
And out degree? Out degrees of A?
3.
3B?
1.
1. D?
0.
E?
3.
3. Right. So now you can see, right? At least, we said at least. Okay. There will be at least one vertex with in degree 0 and at least one vertex with out degree 0. So you have an out degree vertex as well as an in degree vertex. There are two in degree vertices. So now, so what are the applications of these DAGs? So there is a topological sorting and another one is longest path too.
Yes.
So how do we compute the topological sorting and the longest path? So for this graph only, I will explain. So let us take this graph. And for this graph, we don't require the out degrees. It is enough to have the in degrees only. Let us take the in degrees now. So these are the in degrees. So what you have to do is topological sorting is basically you are going to order your vertices in such a way that looking at the edges dependencies. So you are going to treat this direct edge. So this A to D. So this is a direct edge from A to D. So what you are going to do is you have to perform A, or vertex A should be sorted first and then you have to come to D. So it's like tasks. If you treat this vertices as tasks and these edges represent the task dependencies, in order to perform task D, I have to perform task A first. That is what this edge represents. So this gives me the dependency table. So D is dependent on A and we are going to sort these vertices in order according to their dependencies. So we are going to first, so in the sorting, in the ordering, what vertices we will keep at first is which are not dependent at all. So we'll start with the vertices which are independent to any of the vertices, and then from then on we will order those vertices depending upon the dependencies. So that is what topological sorting is, and how it is done is as follows. What we do is for the topological sorting, we will pick, so as this is the DAG, and this topological sorting and longest path to only be applicable on DAGs. Okay. And this is, you have to keep in mind, if we have given you some other graph and if we ask you to find the topological sorting, which is not a DAG at all, and don't be like doing the topological sorting and give something else. So there might be. So I don't say there are options. There might be options that topological sorting is not possible. So like this. So look out for those options also. Okay.
So for that we have to check cyclic things, right? So
First of all, you have to check whether it is a DAG or not. If it is DAG, then only you can compute the topological sorting and longest path. If it is not DAG, you cannot compute the topological sorting at all.
We choose appropriate option then.
Yeah.
So, but
So
in this case, can we draw the DFS?
you can draw the DFS, but it depends on the starting vertex, right? You start from A or E or B or C or
We'll
D.
have to start either from A or E.
No, it's not nothing like that. You can start from B also, but in your DFS tree, you will have only B, C, D. That's it. Okay.
B,
So
C,
that is how it.
This is the directed.
This is a directed graph, right? You start from B. So if you perform BFS or DFS, if you perform BFS, so the next neighbor will be C, connecting neighbor.
And C to D also is possible.
And C to D. That's it. This is your BFS tree and this is your DFS tree also. Okay.
But if we start from A, we can cover most of the vertices.
If you start from A, you can cover most of the vertices. Right.
Except E.
Except E.
And
so
if
it will
we
be like
start
one
from
level.
E, then except A, we will be able to cover.
Correct.
All.
Correct. Correct. Right. Okay. So what you have to do in topological sorting is identify a vertex which has in degree 0. So if it is a DAG, then definitely for using the fact of DAG, there will be an in degree vertex 0, in degree 0 vertex. So identify that. Here we have 2. Pick any one of it. So you can pick A and add it to the topological sorting. And then what you have to do is you have to remove that vertex A as well as the incident edges. So removing a vertex means the corresponding incident edges also you have to remove. So like this. So I will remove this. Okay. And next what I will do is I will update the in degrees. So you see for the vertex B, right now the graph is this. The in degree of vertex B is now 1 only, not 2. So I will update the in degrees. So this, and here also if you see for C, it is not 3 anymore. So one edge is removed. So it will become 2. So you are going to update the in degrees of the remaining vertices. And one more fact of DAG is that if you remove any of the vertex from the DAG, so the resulting graph will also be DAG.
Yes.
Okay? Yes. So that is also one more fact you have to. So using that fact, the second fact, what we will do is we will again have a vertex which has in degree 0. So pick that vertex and add it to the topological sorting. Here the vertex is E. So add it to the topological sorting. So after adding, what you have to do, you have to remove E. Removing E means the corresponding edges also you have to remove.
Sir, we have removed also B.
We have
removed before E.
You how can you remove B? The in degree of B is not 0, right?
Okay, sir.
Before, what is the in degree of B? 1. To identify the vertex which has in degree 0. So among these 4, E has in degree 0. So that is why we added E to the topological sorting and removed the corresponding incident edges also. Okay. And then what we have to do? We have to update the in degrees. So I will update. So you see B, now B has no incoming edges. So the updated in degree of B will be 0. And also C also, you see there is only 1 incoming. 1. And if you see D, there is only
also
1. Okay. Previously I didn't update it. You just correct it. So now again repeat. So identify the vertex which has in degree 0. That is B. So add that B to the topological sorting and remove that vertex. And update the in degrees of the remaining vertex. This will become 0.
So sir, maybe you have touched this, but what does it achieve? Like,
what does it? See, that is what, right? If you have to perform some series of tasks, okay, which task will you perform first and which task will you perform next? So you have to order your tasks, right? Task ordering. So if you are building,
Product manufacturing, like one by one, step by step.
Manufacturing, or you are building an hospital. So there will be a ordered tasks you have to follow. You can't directly paint the walls without constructing the walls. Right? Understood, right? So these kind of cases, these task dependencies, you can draw the task dependencies, and the resulting graph will be a DAG, because if there are 3 tasks and each one of it is dependent on other, you don't know from where to start.
So you have to. So basically, it signifies that you have to do A before E and E before B.
Right.
Okay. Thanks.
Yeah, like that. So now next is the same. So I add C to my topological sorting and I remove C and update these in degree to 0. And finally, I'm left with only one vertex. I will remove that vertex also. And I will add that to the topological sorting. So therefore,
Excuse
topological,
me, sir, if there is no 0 degree of vertex, then what should I do?
Then you should stop doing topological sorting. It will not be DAG.
It's not that.
It's cyclic.
Okay, sir.
Okay.
Some graphs, after you remove one vertex with 0 degree, it creates a disconnected graph. In that case, how do we decide which one to do next?
See, you can pick any one of it. Right now, see, there is one more possible topological sequence is E, A, B, C, D. So if I have removed E first, then A next. Okay, that also can happen.
Yes.
Yes.
Okay. Yeah, this is also a possible. See, that is what this is a possible topological sequence. This is also a possible topological sequence. But this is not a possible topological sequence.
Correct. No,
Yes.
my question, you sometimes you create disconnected graph. In that case, is there any way in which we have to take priority or something? No, right?
No, nothing like that. See, sometimes if you read, there is no priority at all. The only priority is you have to pick the in degree 0 vertex. If you have multiple at a time, you can pick any one of it. It is not like the disconnected one you have to pick. Understood?
Yes, sir.
Sir, as you said, in DAG, level by level, we will be getting a new DAG, right, sir?
Yeah, level by level, you are going to get a
So,
new
is there any chance of, like, initially it is a DAG, and after removing the first vertex, which is having a in degree 0, it will convert it into non-DAG?
No.
Then that will not be a DAG at all.
Yeah, that will not be a DAG, but the chances are there, sir, like.
No, there is no chance. If it is DAG, then definitely this is a fact of DAG, I am saying. So for a particular DAG, if it is a DAG, if you remove any vertex from the DAG, the resulting graph will also be DAG. If it is not a DAG, the resulting is not a DAG, then the initial graph itself is not a DAG.
Right.
Okay.
Okay.
Now this is how you compute the topological sequence. And also other thing is you can also compute the longest path in the graph. So from the word itself, you should understand what we are trying to look. So in the given graph, we are trying to find the longest path, not the shortest path. So we want the longest path in the graph. And by following this algorithm, longest path to algorithm, we will get the longest path in the DAG. So you can get the longest path. So surprisingly, yes, we are looking for the longest path, not the shortest paths. So usually you might have seen many cases, we will thrive for shortest paths. But in this scenario, we will look for the longest path. Why we will look for the longest path is again. So how much, like again in the course lecture it is there. So if you are doing an degree, right now you are pursuing an online degree, right? So how many terms it will take me to complete a few courses? And you know that a few courses have prerequisites of other courses. Again, that is a course dependencies. You will draw the DAG of that course dependencies, and you will try to get the longest path of the graph, and it will give you the minimum number of terms you should definitely go through in order to complete all the courses. So that is where it is useful, longest path to.
Sir, we used to study PERT and CERT, something like that in school. It was similar, no?
Longest
Something similar.
I'm not sure about PER. What is? Can you repeat PER?
PERT, something called
PERT and
PERT.
CPM, sir.
Yeah. Something
That is
similar we
operational
used to do.
management,
No?
like people's.
Yeah. Same thing, right?
I'm completely
It's kind
aware
of
of
same.
what you
Longest
are
path,
saying.
yeah, critical path we used to find out.
Yes. Thanks. Yes.
Wait,
Thanks.
Dijkstra, spanning.
Okay, let us try to compute longest path 2 for this graph. Okay. Yeah. So for longest path 2, we require one more number associated to each of the vertex, which we will initialize it to 0. So let me, in short, I will write LP. So LP of all the vertices is 0. This is the initialization I do. Okay. So what I do, I will initialize one more number and I will associate that particular number to every vertex. Along with in degree, I am having one more number to each and every vertex. Initially, everything was 0. So for all the vertices, it was 0. And now, what I will do is, again, whatever we did in the topological sorting, we will pick the vertex which has in degree 0. So initially we did, we picked A. Now we will pick E. So pick E. So I pick D first. Pick vertex E. And what you have to do is, you add E to the topological sorting. And at the same time, you add the latest longest path value that E has. So longest path of E is 0. So right now we started and we initialized it to 0. So it will be 0. So the longest path to E will be 0. And then what I will do is, I will remove E along with the corresponding edges, incident edges. So I will remove E. Okay, I will remove E and the incident edges. And what I will do is, next step is I have to update in degrees. Definitely I have to do that. Along with that updating in degrees, I have to update this longest paths to also values, LP values. So how I will update is, pick E, remove E, and update LP of I and in degree of I. So it is enough to do for the neighboring vertices. So no need to do for all the vertices. So trivially you can see. So these are the edges removed. So it will only affect A, B, C. It will not affect D. Sorry. It will only affect B, C, D. So E is attached to B, C, D. So it will only affect to B, C, D. So there will not be any effect to A. So it is enough to update longest path of vertex B, vertex C, and vertex D, and also the in degrees of vertex B, vertex C, vertex D. So firstly, very easy thing, we will do the very easy thing. We will update the in degrees. So the in degree of D will be 2, C will be 2, B will be 1. So now, how I will update longest path of I. So I have to update longest path of B, LP of C, and as well as LP of D. So how I will update it? I will pick the max of LP of B, initially whatever it is, LP of B, or LP of whatever just now I have removed vertex, LP of E plus 1. Okay. So max of right now whatever the longest path to B value is there, or the longest path to the removed vertex plus 1. So we will pick the max of these two. So what it will be? Max of, you see, longest path to B as of now is 0, that green number 0. So it is 0, comma, longest path to E. So longest path to E is also 0 plus 1. So it will be max of 0, comma 1. So maximum of 0, comma 1 will be 1. So now I updated longest path of B to 1. So before it was 0. Now I have to update it. So it was went to 1. Similarly, I will repeat for the remaining vertices also. So LP of C will be max of either LP of C only or LP of just now removed vertex plus 1. So even this is also max of 0, comma 0 plus 1. Even this will also give us 1. Similarly, same goes with max of LP of D. Max of LP of D, LP of D plus 1. So again, it will also give us 1. So from 0, everything will be updated to 1. Okay. So whatever we did is just removed E and updated the integers of the remaining vertices and the other number, which is longest path, we have updated like this. We have taken max of either the previous value or the longest path to just now removed vertex plus 1. So whichever is maximum, we picked it. So I will take this graph to down. So right now we have the topological sorting as E and the longest path to E as 0. And next we are going to repeat this process. So we have to find the find the vertex which has in degree 0. So now the vertex which has in degree 0 is A. So what I have to do? I have to add A to my topological sorting and add the LP, longest path of A. Right now, whatever the value is there, just add that value. So it is 0. So add that 0. And what you have to do? You have to remove that vertex and the corresponding edges. Okay. So after removing, what should I do? I have to update the integers. Integers updating is easy. So you can update it directly. So this will be 1. Sorry, this will be 0. This will be 1. And this will be 1. And now I have to update the longest path values. So longest path numbers. So how I will update? So LP of B I have to update. LP of C I have to update. LP of D I have to update. Because A is incident to B, C, D. So how will I update? Max of either LP of B or LP of just now removed vertex is A. So removed vertex is A. We removed A. So LP of A plus 1. So now you see max of just now whatever the value of LPB is there. So right now LPB is 1. So 1, comma LP of A. So look in the row, LP of A is 0. So it is 0 plus 1. So now what we got is max of 1, comma 1, which is 1 again. So you are not going to update it. So initially before this it is 1 and after this also it is 1 only. So max of 1, comma 1 is 1. So you are not going to update it. and we will move to the next thing. So here also max of LP of C. LP of C is 1. Initial before this it is 1, comma LP of A is 0, comma 1. Again you will get 1 only. Similarly, max of 1, comma 0 plus 1. You will get 1. So in this particular graph, even though if I remove vertex A, my longest path to B, C, D is unaltered or didn't change at all. So it's fine. So we will move and repeat the process. So again go to the graph, identify the vertex which has in degree 0. So B has in degree 0. So what you have to do, you have to add it to the topological sequence and add the longest path value of B. So the longest path value of B is 1. And then we have to remove B as well as the corresponding. So now here what we did, we removed. So we remove B and we are going to update. So after removing B, it is enough to update longest path to C because only the longest path to C will change because the edge we removed that only affects C. It will not affect D.
Sir, but can such a long question come in the exam, sir?
Such a long question, matlab?
Sorry, sir. But I think,
we can ask you, yeah, we can ask you like the longest path of this graph is like 5. What will you do? You have to perform the longest path to, right?
Right.
Yeah.
Sir,
So
it
that
is
is
so
why.
lengthy for exam.
No,
No,
it
it's
is
not
not.
lengthy.
Sir is
No,
writing
it is not
everything.
lengthy. I am explaining it
Yeah, step by
very,
step.
yeah, step by step. It's not that lengthy. So if you practice 1 or 2, from third, you by looking at the graph itself, you will say, yeah, from
Right.
E to B, B to C, and D. That is okay.
Okay, sir.
But this is the method and approach you have to follow. If you forget, so if you are
Step by
unable to
step
get the
procedure,
longest
basically.
path, yeah. So the longest path to
Okay.
C will be max of. So whatever the longest path to C is there, or longest path to B, just now removed vertex plus 1. So max of longest path to C is 1. Longest path to B is 1 plus 1. Now it turns out to be max of 1 comma 2, which will be 2. So see now it is got updated. So you will update it. Again repeat the process. So now we have to remove C. In order to remove C, you add the topological sequence C to the topological sequence and the longest path value of C. C is 2. Okay. So you remove it. After adding, you remove it. So you remove it, update the in degree to 0, and I have to update the remove C. After removing, I updated the in degree, I have to update the longest path to D. So the longest path to D will be max of LP of D or LP of C plus 1, whichever is maximum. So max of LP of D right now value is 1, comma LP of C we have 2. So 2 plus 1. So max of 1 comma 3. So we are going to get 3. So that means the updated value will be 3. And what I will do, I will remove this as well and add this to the topological sequence as well as the corresponding longest path 2. So you observe this value 3. So what does this refer? This refers to the longest path in this particular graph you can have is of length 3. So the longest path you can have is at most 3. So this is not a graph. This is the graph. Okay, we have E also here. So the longest path in this particular graph you can have is of length 3 in terms of number of edges. It gives us in terms of number of edges, and that longest path is like this. Either this or you can have one more path.
From E.
Which is this. So A to B to C to D, or E to B to C to D. So both the paths have of length 3. So 3 edges. In terms of edges, we are referring as the path length. So you see, this is the longest path you can get. So the longest path have of length 3. So you cannot get a path which has length 4 in terms of number of edges. And also you can have paths of length 2, length 1, it's possible. But the longest path I can have is of length 3. Okay, and you can compute this using this. Okay.
But if you don't compute and just see this path and can be right.
Right.
You can write.
Okay.
But if we ask you like what will be the longest path value of some E or
Value
some C or
then
then you have to do, right? So then that will be lengthy, right?
Right.
The
So if it
value
is
we can
lengthy,
just add the number of edges, right, sir? Edges, number of the edges.
Okay. So like this. So path length or something like this, we can get from this longest path.
Actually, path length C, if it you ask, then also it is true directly A, B, C or E, B, C, something like that. That is true.
Okay, so that is about Dags, topological sorting, and longest path to an example. So let us see. Let us move to week 12 now. So in week 12,
Sir, do you provide this PDF in the portal?
I will try to provide, but I already said there is an orange cyclone going on. So even though we send it, they might not be available before the systems or to upload it. So it might, there is a 1 or 2% chance of might not get uploaded within the time. So as we are having very less time, so I suggest you to take screenshots or just go to YouTube and you can take screenshots from there also.
Sir, then could you show that that longest path? I will take a screenshot.
Longest path of what?
You want to scroll down, yeah.
This thing.
It's on YouTube as well.
Yeah. Just go to YouTube and take the screenshots now. See, right now it's already 10:54. So many people might
Yes, sir. Okay,
be
sir.
sleepy and they might wanted to learn few more concepts. Okay, let us complete the concepts and then we can. Okay, so let us discuss in short what are these weighted graphs are. So weighted, just now whatever graphs we have seen, we haven't associated any number to edge. So whatever edges you have seen, it's of with no numbers at all. So if I associate a number and call it as a weight of that particular edge, then those kind of graphs are called weighted graphs. So what I said, so if a number is associated to every edge in the graph, and if a number or weight, so usually weight we will refer in terms of numbers only. We will use in terms of numbers. Either it can be negative, positive, or 0. So every edge in the graph, then that graph is called as weighted graph. Okay, for example, like this kind of graphs. So directed, undirected, I am not going to again see it in separate. Let me take it directed only. Even it works for undirected also. So if I associate some weights 2, 1, -1 like this. So if I associated a number to each and every edge in the given graph, that particular graph is called as a weighted graphs. Okay. So this number can represent anything to that edge. It may be the distance or it may be the value or whatever it is, distance, value, What can other be? Other possible. Usually money,
Burning
distance,
time, something
The
if you use.
time. So these kind of things. It can refer to anything, but those values are associated to those edges. Okay. So if you see any number to every edge in the graph, then that graph is the weighted graph. That is how you. Okay.
But
These
I
are
have
weighted
never
graphs.
seen a weight negative actually.
Never seen, huh?
I mean, can there be a negative weight also?
Of course, yes, right? So you are a cab driver. Okay. So
In
this is the
Moses.
amount you spend from traveling from A to B. So you spend some 2000 rupees. From B to C, you spend some 1000 rupees. But while coming from C to A, you have a passenger with you, and he paid you some 3000. But for traveling from C to A, it might have costed you only 2000. So total, if you add the total, so you got 3000, but you only paid 2000.
Okay, yes,
And the
yes.
negative will, so the other 1000 will refer to as negative. That is a profit to you, right?
Okay, right. Got it, sir.
Like that cases, negative also. Okay. So let's have this weighted graphs, and let us discuss this Dijkstra algorithm. Okay. Let me take an example and directly let's look at what is the Dijkstra algorithm and how we perform Dijkstra algorithm. But before that, Dijkstra algorithms are performed in order to compute the shortest path. So here shortest path in terms of weight of the path, not the number of edges, weight of the path. Okay. So in order to compute the shortest path from a fixed source vertex, from a fixed vertex. So I can only compute shortest paths from one vertex to every other vertex. So from one fixed vertex, so we will call it as source vertex. So from a fixed source vertex U to every other vertex in a graph having non-zero edge weights. Sorry, non-negative edge weights. So I am sleepy now. Non-negative edge weights.
Have a coffee.
I will. So in order to compute the shortest paths. So, and the shortest path, not in terms of edges, number of edges, in terms of the weight of the path from a fixed source vertex U to every other vertex in the graph. And that particular graph should not have any negative edge weights. So if it has any negative edge weights, we cannot use this Dijkstra algorithm. So then Bellman-Ford will come into the picture. Okay. So right now, if you don't have any negative edge weights in your graph and you wanted shortest path from one fixed vertex to some other fixed vertex or to every other vertex, then you can use this Dijkstra algorithm. And how we perform this Dijkstra algorithm is as follows. So let me take the example.
So in the previous example where you had minus, we can't use this, right?
No. So if there is negative weight, we can't use that.
Okay.
Okay. So like this. So this is a graph, and I will also give weights to this. So 1, 2, 1, 3, 4, 7, 2, 1, and 6 and 1.
Sir, this algorithm is only for undirected graphs, is it?
Not like that. You can use for directed also, but we more emphasized on undirected only. We can use for directed also.
Okay, sir. Thank you.
Okay. So we emphasize more on undirected. Okay. It's fine.
Okay.
Okay. So how we do is, again, we are going to initialize few things first, and we are going to call it as distance value now. So how I am initializing the distance values? Again, I'm going to associate one number to each of the vertex and call that vertex, call that number as distance value. So initialize the distance values. And how I'm going to do is, because first of all, I have to fix my source vertex. So Dijkstra algorithm will only work for one fixed source vertex to every other vertex. So let me fix my source vertex to be A. So I fixed A as my source vertex. Now what I will do is, in my initialization, what I will do is, my distance value of that particular source vertex to 0, and distance value for all other vertices to be infinite. And this I is actually B, C, D, E, F, that's it, F, B, C, D, E, F. Okay. So all other vertices, I will initialize it to infinite. So again, so my number, I'm going to distance value, I'm going to give 0 to my source vertex and infinite to all other. Okay. Now the algorithm starts. So we'll start the algorithm. This is the initialization we did, and we are going to start the algorithm. So now what I have to do is, from the source vertex, I look at the neighboring vertices and update the distance value of neighboring vertices as like this. So I will update distance value. So neighboring vertices are B and C. So distance value of B as minimum of either the distance value of B or distance value of A plus weight of AB. So weight of edge AB. So I will take the minimum of it. So now, right now, so the value, distance value of B is initialized to be infinite, comma, distance value of A is 0, plus weight of AB is 1. So 1. So I have minimum of, infinity, comma 1. So which will be the minimum? 1 will be the minimum. So I will update the distance value of B as 1. Okay. And I have used this edge. So you no longer have to go back and check that edge, and check that edge in order to check that whether the shortest path will change or not. So no need to go back to that edge. So with respect to that edge, we have updated our distance value of B. So similarly, the other neighbor is C. So the distance value of C, I will update to min of distance value of C, comma, distance value of A plus weight of AC. Okay. So what it will be? So minimum of distance value of C we have initialized to infinite. Distance value of A is 0 plus weight of this edge AC is 2. So it will be 2. So minimum of infinity comma 2 will be 2. So I will update my distance value of C to 2. Okay, this is done.
So it's a kind similar to the longest path where we have taken non-weighted graph and as equal to 1. 1. So instead of 1, we are taking the weight of the AB. That's it. As
right.
That's it.
So weight of the AC. But there you have looked for max. Here you have to look for min.
Shortest.
Okay, shortest. Right. Okay, you can connect it like that. Now, once you are done with A, just go to the any one of the neighboring vertices of A. So you can go to B, or you can go to C. So move to B or C. Fine. Let's move to B. Both will give you the same answer. So move to B. And what you have to do is you have to update the distance values of the neighboring vertices of B. So neighboring vertices of B are D, C, E. So you can check via edges. So there are 3 edges. So there will be 3 neighbors. So how I will update? So there are 3 neighbors. Distance value of C, distance value of D, distance value of E. So how am I going to update? I'm going to update, consider minimum of either the distance value of C, comma, distance value of B. Right now I am at distance value of B plus weight of BC, edge BC. Okay. So what it will be? Minimum of distance value of C right now is 2, comma, distance value of B right now is 1, plus weight of BC is 1. So 1. So minimum of 2, comma 2. That will give you 2. So like this, I will update minimum of. So distance value of D is infinite. So I'm writing it directly. And next distance value of B is 1 plus weight of BD. So this edge, weight of BD is 3.
Sir,
So minimum of.
sir, can I do without like these things to see the graph and A to B to D? 1 plus 3 is 4.
Right.
You can see like that also,
So
but
the
that may not
maximum
be the
capability
minimum.
is right.
But
Okay.
that may not be the minimum, right? So if you go to B first, that doesn't mean that that will give you the shortest path. So here
So what
itself
we
in the
can
example
do,
you can.
what
Here
we
is the
can do, we
example,
can.
right?
Okay, goes.
Yeah,
Sorry.
yeah. Here itself you can see shortest path to D will be this A to C, C to D, which is of length 3.
Okay, sir.
Yeah.
Okay.
Understood,
Yes.
right? Right now we have updated distance value of D as 4. So right now we got it as 4. So we are going to update it as 4 for the time being. So this edge we have explored, this edge also we have. And again, distance value of E I will update to min of infinite, comma, distance value of B is 1 plus the edge weight of B, which is 7. So it is min of infinite, comma 8, which will be 8. So I will update E also to 8. Okay. Next I will move to C. Okay. So A is done, B is done. Next I will move to C. So once I move to C, again I will look out for the neighbors of C. Unexplored or unvisited or untraveled neighbors of D.
Sir, if we would have picked C before D and we would have calculated a distance value of E, it would have been 4, right?
Yeah, it would have been 4.
Okay.
Yeah, it would have been 4. Okay. So let me take this graph down. So right now the graph looks like this.
So in 95% of the scenarios, the sum of the paths will be the distance value, right?
Sum of the path will be the distance value, and it will give me, as we are taking the minimum, so it will give us the, out of all the possible paths, it will give us the minimum shortest path. Okay.
Because let's say that we get a question.
Let's say that.
Let's say that we get a question like this in exam. So that min max, it will take a lot of time. So isn't it convenient or better or less time consuming? I know in scenarios it might not be true, but to add the edges distance and then arrive at the distance value.
Yeah, you can add the edges and distance value. But always it will not happen, right? See, right now you just went to B and the distance value of D is 4, correct? So it's not that final value of D will remain 4. And as this graph is very small graph, for explanation purpose, I have given this 6 vertex graph. If it is long, there will be many paths to reach D. Right now, there are this path, ACD path, there is ABCD path, so only 3 paths. Or there is paths like this, ACED, and there are paths like ACEFD. Okay, out of these many paths, which one will be the shortest path? How will you know that? So whatever the path you pick first, that will not be the shortest.
Okay, I get it. Yeah.
Okay, yeah.
Sir, there is this Kruskal algorithm, no? So can we use that here, wherein it takes the minimum weights of the edges and it calculates?
See that Kruskal.
It arranges in a particular order and.
No. First of all, understand the purpose of the algorithm. So what is the purpose of using Dijkstra algorithm?
To find the shortest path.
Shortest path. And what will be the purpose of using Kruskal's algorithm?
Minimum cost spanning tree.
Minimum cost spanning tree, right? Right? How can you guess the shortest paths from one fixed vertex to every other vertex by computing minimum cost spanning tree?
But minimum cost also we use the weights on the edges and.
We will use, but do you think finding minimum cost spanning tree will give you the shortest paths to every other vertex from A?
Okay.
So I will use the same graph for computing minimum cost spanning tree also. Then you will get to know.
Okay, sir.
Okay. Yeah.
Yeah.
So we'll proceed now. So now we are at C and we look out for the neighbors of C and we will update the distance values.
Sir,
so I'm updating
are you going to cover all the algorithms?
Not all the algorithms. I'm not going to cover Bellman-Ford and Floyd-Warshall. Okay. I already told in the initial stage only. So if you wanted to go through Bellman-Ford and Floyd-Warshall I discussed in the previous session. Complete session I spent for Floyd-Warshall. So you can watch it there.
Okay.
And for Bellman-Ford, you just solve some problems.
Please, ma'am, Kruskal algorithm will be discussed. Prisma in spanning tree. Prisma
Prims and Kruskals we will discuss. Okay. Okay. Right now we are at C, and now we will compute the distance value of D as min of distance value of D comma distance value of C plus weight of CD. Okay, it's like I'm writing it directly now. So min of initially the value is 4 previously the value is 4, but right now the value will be distance value of C plus weight of CD is 1. So minimum of 4 comma 3 is 3. So you have to update. So now the distance value of D has changed from 4 to 3. Okay. In considering this side. Fine. Again, you have to update D B of E also, because E is also neighbor to C. Yes, so how I will do min of initially whatever is there, comma dV of C plus the edge weight of C. So this will be min of 8 comma 4, which will be 4. So again the updation will happen and it will become 4. And this is edge is also, and we have seen this edge also. Okay. So now we will move to vertex D or vertex E. So let us go to vertex D. So whichever, it's fine. So vertex D. And once if you go to vertex D, we will look out and update if there is any shortest path is changing if I consider this edge or this edge. So that I will update. So dv of E, I will
Sir, we have
update.
understood these things. Can you go the
Move.
next
Shall I
topic?
move? Okay, sure.
Yes,
If
sir.
everyone is okay, I will move. Is it okay?
Sir, how
Shall I
will
move?
what will be the final answer?
No, sir.
Final answer, it
I'm
will
not
be like
okay.
5. This will get updated to 5.
So typically we will have questions from one vertex to any other vertex in this, correct?
Maybe like, yeah. So maybe we can ask you like, what is the shortest path, or what is the minimum cost I have to spend in order to reach from A to F, or A to D, or B
Okay.
to F, kind of things. So when we ask from B to F, so you have to start from B and you have to compute the Dijkstra algorithm to E. So you have to compute the shortest path from B to F. So then you will get the value, distance value, whatever the distance, final distance value that F has will be the shortest path. Right? So
So now the final value is 5. So the shortest path is the number of edges.
Not the number of edges. The shortest path is this path. A to C, C to E, E to F is the shortest path in terms of
Edges.
weight of the path.
Weight of the path, okay.
The weight of the path is 5.
Okay.
And this 5 is this 5. So in order to reach F from A, you have to spend 5, or you have to travel 5 kilometers, or like that.
Okay.
Okay. Minimum you have to travel. So that is the shortest you have to travel. Okay. So that is what Dijkstra will give you. Okay. So in that case, we will move to spanning trees, and this is the last concept I have.
Sir, it can be A, B, C, E, F also, the last two shortest path.
A, B, yeah, it can also be A, B, C, E, F also. There are two paths which are of same length. Okay. So spanning trees. So why we call this spanning trees is because these trees are spanned from a graph. So if I have a graph G, if I have a graph G, what I am going to do is I am going to span a tree out of this graph. So how will I span a tree? So if the given graph is not a tree, what I will do is I will remove some edges and make the graph as tree. So I will take the subgraph of this G. So by removing few edges, I will try to come up with a tree which is spanned from this graph only. So for example, this. So we'll take this example. I will draw. So the same thing. So you know the properties of tree. What are the properties of tree? What is tree basically?
Minimal connected acyclic graph.
Correct. Minimally connected acyclic graph. Okay. So that means if I remove an edge from the tree, that will fail the property of connectedness. If I add one more edge to the tree, it will fail the property of acyclic. So it will form a cycle. So okay, this is the minimally connected acyclic graph. So if I add one more edge to it, it will no longer be a acyclic graph. It will become cyclic graph. Okay, that is why minimally connected. So now I have to span a tree from this graph. So how can I span? So spanning a tree requires, it is just the subgraph of this. So right now this is not a tree because there are many cycles. So I will try to eliminate the cycles and try to bring the tree. So from this I can have this. So if I had this edge also in my tree, that will become a cycle. So I will not have this edge. So I can have this edge. I can have this edge. And I can have this edge. And if I try to have one more edge, like this or any edge, it will
It will
get
become a
snapped.
cycle.
Yeah, it will form a cycle. So this is a spanned tree out of this graph G. Okay, so this is not a tree now. This is a tree, of course, but we will refer it to as a spanning tree. Okay, why we refer to as a spanning tree is because this is not a self-built graph. This is actually spanned from the previous graph G. This graph G, it actually spanned from this graph. So that is why every spanning tree is a tree, because every spanning tree satisfies all the properties that tree satisfies. So every spanning tree is a tree, but not every tree is a spanning tree. So not every tree is spanned from some other graph. Right? Correct?
Yes, sir.
Right? So that
Yes,
is why.
Sir.
That is why.
Sir,
Just
the
remember.
graph is a spanning graph or not?
Which one?
In the second graph.
This is a spanned graph, spanned tree. This is the spanning tree.
Okay.
Spanning tree of G.
Sir, can you repeat? Sir, can you repeat how it is spanning tree?
So it is spanned from this G, right? So what did we do? We just took the subgraph of this G. By removing few edges, we have come up with a tree which actually the subgraph of this G. Subgraph meaning we are having few edges, not all the edges. So you know the subset, right? All the vertices should be there.
And should be connected.
I can go from C to E also.
We want to go from
one by one.
No, we should be able to go from any vertex to any vertex, right? That is what
any vertex to any vertex. So that is how it is connected, right? Connected means you can travel from any vertex to any vertex. Okay. So whatever you span a new graph, that should be connected, and also it should not contain any cycles. So
Sir,
connected without cycles means it is tree.
Sir, if we connect to A to F, then it is a spanning graph or not?
It is a spanning A to F. How can it be spanning graph? In the original graph itself, there is no edge between A and F.
Okay, sir.
But here, sir, instead of removing C to E, we can even remove D to E and retain C to E, right?
That is fine. That is different. That spanning trees you get for, there are many spanning trees.
Okay.
You get for a graph. Okay. So that is why there is something called minimum cost of spanning trees. Out of all possible spanning trees, which spanning tree
choose the minimum
cost
one.
is the minimum? Yeah.
Yeah. Okay.
Sir, and BFS and a DFS tree can also be a spanning tree.
Yeah, very good. BFS and DFS tree for an undirected graph forms a tree, spanning tree. They are spanning trees of their respective original graphs. Okay. Yeah. So that is how. The spanning trees are always spanned from an original graph. So there is a graph, and this tree is just the subgraph of that original graph. Okay. Now.
Okay, sir.
This is about spanning trees. Now, if I have weights to my graph, and then if I wanted to find the minimum cost spanning tree, now just now I said there can be more than one or more than two spanning trees for graphs. So there can be more than one spanning trees. Out of those spanning trees, which spanning tree, the tree cost is minimum? So let me explain the tree cost also. So let us see. 1, 2, 3, 1, 3, 2, 1, 4, 2. So it is like this, and I have spanned a tree out of this graph, and these weights are 2, 4, 1, 2. So the cost of the spanning tree will be, so whatever the edges you have in your tree, the weights of those edges you have to add. That will be the cost of the spanning tree. So the cost of this spanning tree is the cost of spanning tree. So ST means spanning tree will be 1 plus 1 plus 2 plus 2 plus 4. So this
Sir,
will
it is
be
better from
10.
Dijkstra algorithm, sir.
Sir, from Dijkstra algorithm, we can easily
So I
get this.
didn't bring prims and Kruskals yet now, as of now. So I have a graph, weighted graph, and I just took a random spanning tree. So this is a random spanning tree, and I just computed the cost of the spanning tree. So the cost of the spanning tree will be 6 plus 4, which is 10. Okay, and I will pick one more random spanning tree. Even this is also a spanning tree.
So every tree is not a spanning tree, right?
Every tree is not a spanning tree, right?
Okay.
So it may not have spanned from a graph. It's actually the graph. Maybe it is the graph. Okay. So this is one more. So 1, 3, 4, 1, 2. So this is one more spanning tree of this graph G. So cost of this spanning tree will be 1 plus 3 plus 4 plus 2 plus 1. Which
11.
is 7, 9, 11. So you see, each spanning tree will have a different cost, or may not be. Some spanning trees may have the same cost, but spanning trees, if there are some 10 spanning trees, all the 10 spanning trees will have cost to it. And out of those 10 spanning trees, which one is the minimum? So it is very difficult to draw all the spanning trees, all the possible spanning trees, and compute the cost of each and every spanning tree, and then take the minimum of it. It will become a very lengthy process. Instead, we have few algorithms. If we follow those algorithms, if we perform those algorithms, we can directly get the minimum cost spanning tree. So the spanning tree which has the minimum cost. Okay, so two of those algorithms are prims and Kruskals we have discussed. So both algorithms are used to find the minimum cost spanning trees, and both will give the same answer. Okay, if you have performed prims algorithm and you got the minimum cost of the spanning tree as some 12, even if you perform Kruskal's algorithm, the minimum cost of the spanning tree will be 12 only. So you will not get something like 11 in the Kruskal's algorithm and some 10 in the prims algorithm. Okay, so whichever algorithm you follow, the minimum will always be the same. And this is how we will compute the minimum cost spanning trees. So I will discuss. So which algorithm should I discuss? I will take the poll. The other one, both are easy.
Whichever is important from exam.
Whichever, see, that is what I will leave it to you guys. Whichever you feel is easy. You take that algorithm. You learn that algorithm.
Useful for future.
See, both has pros and cons to it. So if you ask my opinion, I prefer Kruskal's. Because I feel
Okay, sir.
is easy.
Okay, sir. Then Kruskal.
Okay, sir.
Okay.
Kruskal, sir.
So what Kruskal does is he arranges all the edges in the ascending order of weights, in the numerical order, increasing order of weights. So what he will do is he will see the graph and he will arrange. So this is the first edge, AB with weight 1, CE with weight 1, DE with weight 1. So like this. So after that, he will go to the weights of.
Sir, we have
two
not
weights.
attached any weight for DC, CD.
Okay. 5. Okay. So next comes weights of 2, AC, BE, DF, and then comes BC and EF, and then comes BD. So we will arrange all the edges in the increasing order of weights. So BD and finally CD. Okay, so let us call this. This is our edge set. So we have arranged this. Now what I will do is I will develop my tree, spanning tree. So I will take all the vertices first because my tree should contain all the vertices. D. So now what he does is he will go in this row, in this line. So what he does is he will add this edge to the spanning tree, first edge to the spanning tree, if and only if it doesn't create any cycle. So for the first two edges you can add directly because with the two edges you definitely cannot form a cycle because for a cycle you need at least three edges. So first A, B and CE you can add. Okay. Now next move to the, so this edge is added, this edge is added. Next move to the next edge, which is DE. So if I add DE, if it creates a cycle, then I am not going to add that to my spanning tree. If it doesn't create a cycle, I will add it. So DE doesn't create a cycle, I will add it. So okay, I will add. So now AC. So next is AC. So if I add AC, if it creates a cycle, I will not add, or else I will add. So AC, I will add. So AC, I will add AC because AC doesn't create any cycle.
So for adding any edge, the rule is that it should not create a cycle, right?
It should not create a cycle. Next we will move to BE. So next is BE. So if I try to add BE, so what happens is
it will
creates a cycle now.
Yes.
So BE, I will exclude. I will remove BE. I am not going to add it. I will move to the next edge. Next edge is DF. So if I add DF, it won't create a cycle. So I will add DF.
Yes.
So like this I proceed. So DF is added. Next BC. So if I add BC, it will create a cycle. I'm not going to add it.
Now actually anything you add will create a cycle.
Anything you add will create a cycle because remember the properties of tree. Tree properties will help you. So for a tree, if I have n vertices, that particular tree will have n minus 1 edges. So I have given you some 6 vertices here. So it is enough to get 5 edges in your spanning tree. So if you got 5 edges, you stop it there. So we got the 5 edges. And the cost of the spanning tree is the cost of this particular spanning tree will be
7.
Yes. So 1 plus 1 plus 1 plus 2 plus 2, which is 7. So which is minimum than this 11 and 10. So even these are also the spanning trees, but these are not the minimum cost spanning trees. This is the minimum cost spanning tree. Even you perform prims. Prims is also okay, easy only. I don't say that is very difficult. Just go through prims also. Even you perform prims algorithm, you will get the same cost. Your cost of the spanning tree will be same. And think about this. What if I say I have given you the cost of the spanning, minimum cost of the spanning tree, and I have given some variable somewhere here. I said X. Okay, what are the possible values of X? You might have seen these examples also.
Yes, sir.
Okay, so we can give vice versa also. So what are the possible values of X? Like that. Okay. So this is about, these are the important things I wanted to discuss. And
Sir, in Prim's algorithm, we need not to check for cycle.
We need not to check
For cycle, whether it is forming cycle or not.
We have to check, right? Even prims also you have to check. If it forms a cycle, you are not going to add that.
Sir, it's both seems to be same. We are starting from smallest weightage. Also, we are doing in Kruskal. We have already sorted, so we are starting with the smallest weightage.
See, Kruskals we follow the minimum edge weights, okay, and prims will follow the connectedness of the tree. So the spanning tree must be connected, okay. So prims will follow this idea. So he will take the least weight first, and then definitely this particular edge should be connected to some other edge.
Yes, sir.
If it is not connected, then it will not be a connected graph. Our tree is anyway connected, so definitely there should be a connected edge to this particular minimum weight, and that particular connected edge also we will pick the minimum. So prims will use the connectedness of the spanning tree, connectedness of the tree property.
Yes, sir.
Okay.
It grew after choosing a smallest one.
Yeah, it's like it will grow. And Kruskal is like he will start randomly by picking the least weights first, and then the next weights, next, and he will order it in the increasing order.
Kruskal already understand that it will already connected. If it does not create cycle, it will be get connected.
It will get connected. So he will use the cycle property mainly. So without looking at the cycle, so without creating cycles, he will build the tree. And in prims, he will use the property of connectedness as well. So he will use that connected thing and he will proceed. So both ways will reach the same answer. Okay. And yeah, so whatever I wanted to discuss, I have discussed. And I hope you all will do good in the final exam. And I suggest you
Sir,
to
can you
more
tell me
focus
the
on graph
question?
theory. Yeah, I will
Sir,
take questions. Okay. Those who wanted to leave, definitely it's already 11:40. You can leave.
Sir, can you just tell me like
Sir,
how much
I have
portion
a
will be
doubt
asked
in
from like week 9 to like week 9, 11 till last portion? How much?
It's already given, right? From graph theory itself, you will get some 35 to 40%.
Okay.
Okay. And
And
I
then
can also tell you the number of questions also. There will be 5 questions out of some 14.
okay, sir. What about from week 5
mail
to
has come,
8?
sir, already. Please, already 11:45.
Okay. Yeah. So you just check the mail, na? So with
Okay,
term
thank you.
weightages and the number of questions, everything has been sent to you.
Sir, how many
Okay.
questions will be there?
Madam, please check
Okay.
mail, madam.
Huh?
Five
Could you please
question.
explain
Can
mock
you take one
7?
question from the mock, sir?
Yeah, mock 7 third
Sir,
question.
mock
Please.
last question, that coloring problem, sir. I am not able to get that. I am getting answer as 4. Can you just give me the solution, sir?
4 is the
Answer
right
is the 4. 4 is the right answer.
I
We
got
have discussed.
3.
Sir, they have told answer.
I got 3.
Sir, answer
You
is
got
given.
answer was
Answer is
wrong.
given. Accepted answer is 3, sir.
I got
understand.
3.
I understand. You got 3, Rohini. Can we
Yes,
discuss that?
I'll just show you.
Sir, actually, I'm waiting for this only. Now you are telling it is 4 only.
See, this was discussed in the beginning of the session.
Okay.
I was not in that started late. So answer is 4 only, sir.
See, the
sir.
same
Good night,
question
sir.
is given in the mock 7 also. So there it is given it as 4, it seems. So the answer will be
sir.
4 only. Yeah.
Good night,
Sir,
sir.
could you give a gist of mock 7 question 3, please?
Yeah. I will now take the mock questions. We will discuss few mock questions and we can end the session. So those who are done, you can leave and have a great night.
Sir, can you
And
please
prepare
explain
well
the
for
question
tomorrow.
number 6 from mock?
Let me open mock first. Okay, give me some space to open. Okay. I'll just take. So
No, I made a mistake. I think the number of colors is 4 only.
So
I
mock,
made one mistake over here.
Mock 7 third question.
Okay. So we will discuss mock 7 third question first. So first question is okay, right? Mock 7. So let me share the screen. Just let with screen itself we can.
Sorry.
So let me just one more minute. Let me share the screen.
Because we don't have the solution for this mock 7 also.
Yeah, I understand. So where is this one? Let me new share.
I did not get any intimation about the mock, so I had not been. I could not attend the mock.
We have been sending mails and announcements.
No, I did not get any email or WhatsApp message for the mock.
Okay, then I think you have to check with support team. Okay, so first one is like this. A vertex is U is called a root vertex.
Yeah, first,
of a
second
directed
one
graph.
easy only.
This was okay, right?
Third one, I don't know how to approach it actually. It's a
Second,
big
yeah,
problem.
third one we will discuss. So they say, so we will directly discuss the cases. Okay. Case one says nodes represent the locations of employees, okay, and edges represents the roads connecting these locations, okay.
Okay.
And each cab can pick up employees from only one location, okay. Sanya need to arrange the minimum number of cabs under the assumption that each employee is willing to walk at most one road length from their current location to a neighbor location to be picked. Okay. Now see, if the cab is at this point, who all is my cursor visible?
Yeah, it's visible.
Yes, sir.
Yeah, it's visible, right? If the cab is at this point, who all can board this cab? This guy.
Maybe all the adjacent.
Yeah, all the this guy,
nodes.
this guy, and this one.
Yes.
So four places, and along with this place. So if I arrange a cab at this position, I can cover 5 places, 5 locations, right?
Yes.
So like this, you have to find. So if you find, you have to also find the minimum number of such locations. So I think you will get this location. If I pick this, I have to pick this as well as this, I guess. Okay, so this, and this. So it is sufficient to pick 3 locations, and these 3 locations will suffice my need. So if I kept at this point, this location people and this location people.
So it will be like concept of vertex coloring, or?
No, it's not. It's nothing. It is not vertex coloring. It is not vertex cover. It is just the case. It is just one particular case.
Okay.
Okay. Why it is not vertex cover? Because see, there are many edges. This edge is not covered. This edge need not to be covered. Okay. Given cases, I can have a cab here, cab here, cab here. Done. With 3 cabs, I can ask the other people can walk at most one road and come and board the cab. Okay. So that case one is some case, but it will not be a general vertex cover or minimum coloring or something.
So just looking at the graph, we need to decide.
Fine. Yeah.
Okay.
And the next case is easy case only, I guess. It's vertex coloring case. Do I need to explain that also?
It's okay, fine, sir.
It's okay, right? Just read
I thought we need to relate some with some concept like.
No. There is nothing in this.
Okay. Thank you so much.
Next. Yeah. This vertex coloring,
mock
right?
9.
I will move to mock 9. So this is the graph I guess you are asking about. So vertex coloring of this graph.
Yes, sir.
This is 4. So DFS, you can compute. And like this. So given a DAG, what are the possible topological sequences are? And the longest path in the DAG has length 4. So these all things you can do now. Right? So do it. Even now a square, compute a square, and a square table is also will have 0 or 1 entries. And 8, 9. So 9 is actually again the oil deposits burning of time taken. So it's like Dijkstra algorithm, and you have to give the order in which the oil deposits will burn. So you can use the Dijkstra algorithm for this. And finally, a railway network connecting 8 towns. This is referring to which one?
Minimum cost spanning tree.
Correct. So you have to find the minimum cost spanning tree, and that will be the answer. So this is regarding mock 7. So let me move to mock 9. So the final mock.
Sir, question number 6 and 8.
So question number 6 and 8. So first one is okay.
Question number 5.
Yeah, let me walk through all the questions. Question 1 is okay, right? So you know the
sir,
properties
please
of logarithms.
explain, that
I
graph,
have to
please.
explain.
So,
No
because that
need, sir.
inverted graph.
Okay, okay. Think it like this, na? So logarithm will never be inside log. It will never take negative values, right?
Yes,
or
sir.
no? Log
Yes,
inside
sir.
something will always be positive,
Yes.
right? So that means my minus x square plus 14x minus 45 should be positive. I should only pick. So I will have a graph in the region where my minus x square plus 14x minus 45 is positive.
Yes.
Yes or no?
Yeah, yeah.
Yes.
And in which region minus x square plus 14x minus 45 is positive is draw the quadratic graph. So it's an inverted up down,
Upward
right?
parabola.
Inverted
Okay, downward
parabola. It is minus x square. Okay, it will be a downward parabola and in particular region the parabola will be positive. Yes or no?
Yes. Yeah.
Yes.
Right. And that is the region you will have a graph for this f of x.
Okay.
Right. From there you can get it. Okay. And use the properties of logarithms also. So what happens when the inside thing reaches to 0? It will go to minus infinite, right? So what happens? Minus x square plus 14x minus 45 is approaching to 0. So log of some 0.001 is a negative, very much nearer to infinite, minus infinite, right? So you require some knowledge of properties of logarithms as well as properties of quadratic functions. Then you can predict the graph.
And
okay.
sir, natural number will include 0, sir.
Yeah, natural number will include 0. So this was I guess I have taken the very first session and I said from here onwards just forget whatever you learned in the class 11, class 12. Okay. Now question 2 is also okay, right? So these questions you might have seen many till now. And what about question 4? Question 4 also you can easily get. You can find the domain of a composite function.
In the question 4, this range, the domain which has been given is 2, 3 union 4, 5. So is the domain from 2 up to 5?
This option can be explained, sir.
That one we can draw polynomial graph from the
See,
graph we can do it directly.
You should know the property of square root. Square root inside also negative values
Greater
are
than
not allowed.
0.
Yeah, inside value this should be inside polynomial should be greater than 0.
Yes, it should be
So
greater.
find for what values of x the inside will be greater than 0. So that will be the domain.
Okay.
Okay, draw this polynomial graph and look for those x's which will give me the positive value. Okay, that will give us 2 to 3 and 4 to 5.
Okay.
Okay, like this. And what happened to 5? 5 is also okay. Just plot the points and find the distance.
Distance.
And 6?
Sir, I have a doubt in 6th question.
Yes, sir, me too.
What was the doubt?
Sir, I can't understand this CX equation.
Okay. So what the company says, a company wants to manufacture iron rods. Okay. Before they start production, they estimate the total cost C for producing X number of iron rods is some 0.2 into X plus 1000. That means if I have to produce some 10 iron rods, my cost of producing 10 iron rods will be 0.2 into 10 plus 1000. So how much it will be?
Yes.
2 plus 1000, 1002. Right?
Okay. Yes, sir.
So cost of producing 10 iron rods will be 1002. So like this, if I have to produce some 100 iron rods, so what will be the cost of producing for 100 iron rods? 1020. 1020.
1020.
Correct?
Yes, sir.
Like this. If I have to produce X number of iron rods, then the cost will be 0.2 into X plus 1000. So that is how. X is a variable here. X is like 1, 2, 3 number of iron rods you produce and their corresponding cost. If you produce one, C of 1 will be the cost of producing one iron rod. Like this. Okay.
Okay, sir.
And next is the total revenue for selling X number of iron rods is R of X is equal to 2.5x. So this is the cost of producing those many number of iron rods. And this is the, if you sell those
Total
number of
revenue.
iron rods, you will get the total revenue. Okay, this is the total revenue. And they are also sure that every iron rod produced will be sold. So if I have produced some 100 iron rods, okay, and
Yes, sir.
the cost of producing 100 iron rods will be 1020, and I will get total
Yes, sir.
revenue as 2.5 into 100, which is 250, right?
Yes, sir.
I spent 1020 rupees and I got only revenue which is of 250. And will I get a profit or loss?
Loss.
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 And loss, right? By producing only 100
Yes.
iron rods, my cost of producing 100 iron rods is like it cost me 1020.
200.
So what you have to find the minimum number of iron rods the company should manufacture to get a profit.
Profit.
So what that means? So you have to find the minimum value of X for which this 0.2x plus 1000 is less than 2.5x. That is the idea. Your
Equation.
revenue should be greater than the cost produced, production cost. Okay. So for what value of X you have to find. So you just use the less than symbol. It will be easy. So 0.2x plus 1000 should be less than 2.5x. You will get the answer. So bring that 2.2x to the right hand side and you will get something like x greater than something.
Okay, sir.
Got it, sir.
So minimum will be least. You have to pick the minimum. So seventh one is also okay, right? You have to just draw the graph. So increases, decreases, and everything.
Sir.
And eighth one is
Sir, 8-1.
In seventh question. Sir, what is the difference between option number 3rd and the option number 4th? When I have calculated, the equation is same.
Equation is same, is it?
Yes, sir.
No, no. X plus 30, X minus 30, X minus 10, X plus.
Sir, the roots are different.
Roots itself is the different, right? The roots of f of x is like here it is like minus 30 and plus 10. Here it is 30 and minus 10. Right? That is different graphs.
Okay, sir.
Check. And what about 8th?
Yes, sir, I am having doubt in 8th.
What is
Sir,
the
how
doubt?
to solve it?
How to solve? Okay. So you have A. What is A? Maximum of. So you are supposed to find the maximum value of 5 log 100 mod sine 2x to the base 10. So for this, when will 100 mod sine 2x be? No, I am not writing anything. So I will explain it here. So if sine 2x attains the maximum value, this log of base 10 will attain the maximum value, and 5 times of that maximum value will give us the maximum value. Correct?
Correct.
Yes.
So the when will mod sine 2x will attain the maximum value? So what is the maximum value of sine 2x?
N pi by
Minus 1 between 1.
1.
See, sine 2x value. I don't want at which position. What is the maximum value?
5 degrees.
N pi by 4.
N pi by 4 is at
X is equal to 45.
Okay, x is equals to 45, but I want the maximum value. What will, if I substitute 45, what will be the value?
1.
So sine 2x can take maximum value as 1.
1.
Right? As there is mod, even though -1 also will give me the maximum
Yes,
value.
-1 will also be 1.
But anyway, both will give me 1. Modulus of it will give me 1.
1.
So log 100, so it is like 100
Square.
times 1, it will be 100. So log 100 to the base 10 will be
2.
2. So 5 times 2 will be
10.
10. So the value of A will be 10. Okay. Similarly, you come here. So B is basically minimum of this log 10x square minus 40x plus 50 to the base 10. So in order to get the minimum value of log, so you know the log properties, right? So if x is minimum, log x will also be minimum. Do you know this? So log is actually an increasing function, right?
Yes.
Yes, sir.
So if I take lesser values here, my log of that also will be lesser. Right? So in order to get the minimum of this, it is sufficient to get the minimum value of this quadratic function. Right? So if I have the minimum value
Yes,
of this
sir.
quadratic function, then log of that minimum value will give me the minimum value.
1.
So you have to find the minimum value of 10x square minus 40x plus 50. What will be the minimum value? So use minus b by 2a.
Base 10 of 10 into bracket x square minus 4x plus 5.
It will be 2.
If we take 10.
So you can use
10
that minus b
common,
by
sir.
2a, right? So this is an open upward parabola. You are going to have a minimum value. So at x is equals to 2, you are going to get the minimum value. Just substitute x is equals to 2. So 10 into 4, 40, minus 40 into 2, which is 80. So 40 minus 80 minus 40, minus 40 plus 50, 10. So log 10 to the base 10 will be 1. So the minimum value of b will be 1. So value of a we got is 10. Value of b is 1. So now do this. So what this says, log 10 minus 1 to the base 10 times 1. So log 9 to the base 10. Right?
It is 0.
So log, what is log 9 to the base 10?
Log 3 square.
0.9 something.
It is 2 log 10. Sorry. 2 log 3. 2 log 3.
What is 2 log 3?
So log, you said log
It's 0.95.
9 to the base 10, no, sir? So it is log
will be a
9
little
3
less
square.
than 1.
Which one is less than 1?
A minus b.
A minus
Log
b
to
is
the
10
base
minus 1,
AB
right?
of a minus b
That's
will
what,
be
sir. So
more
log
than
9
0.
3 square, you can put 9 as 3 square.
Ah,
And that will become 2 log 3.
2 log 3. Okay. Anyway, it is positive, right?
0.95.
Yes, sir. Point something the value is.
0.92.
Yeah. So it will be positive. Unless, see, when will log go negative? Unless this a minus b goes less than 1. Okay. If a minus b is greater than 1, you will definitely have the positive values. Okay. Greater than 0. So log a minus b to the base ab is greater than 0. Similarly, just substitute. Just we got a and b values. Then substitute and check whichever option is correct. So why this is not defined? So you see here it is given b minus a. 1 minus 10 is
minus 9.
minus
1
9.
minus 10 will be minus 9.
Right.
That is why
So
it
that
is
is
not
why
defined.
it is not defined like this. Is a plus b is equals to minus 11?
No.
No, it is
It
plus
is
11.
Plus 11. So that is why it is not a correct option. Okay. Like this you have to do. So this you can do, right? Just remove the modulus. then you can get it.
Sir,
And this also very easy.
whenever a function is continuous, it need not be differentiable, no?
Right.
So, for example, if they ask whether this particular function is differentiable, what is the steps to be followed, sir? Or is it that limit h tending to 0 f of
See, in order
a
to
plus
use
h?
that also, so I'll just show you. Right now I can't search, but I will just give you some insight how you have to look at some tree kind of thing. Okay. So
Okay.
So what you have to do is for checking limit continuity.
The Riemann sum method is remaining.
Riemann didn't discuss at all in the previous session. Yes, no. I just want some input.
Yes, sir, you discussed.
They discussed, is it?
Yes.
So Riemann, don't worry about Riemann
One
too much.
tutorial
Okay?
has it, sir. One tutorial has the Riemann sum.
Yeah, I discussed one tutorial. You can just go watch the tutorial. Okay. So how do we use? Where do we use Riemanns actually? So it's tutorial 10, I guess. In week 9, tutorial 10. Yeah, thanks for reminding. So if you want that Riemann sum, just go look at tutorial 10, week 9.
It has left hand Riemann sum, right
And I will
hand
give
with
you just focus on left, right. Okay. So don't be much worried about trapezoidal, midpoint. Right now, don't worry about it. Okay, focus on left and right.
You discussed in
limit-
end-term revision 2 also on 7 December.
So you can just go to that also. Okay. So for this, what you have to do is you have to check, you have to start. And what you have to check is, first checking is the left hand limit is equals to right hand limit or not. Okay. When I say left hand limit, I mean so limit extends to some, if I am checking at a, let us say a. So a minus f of x is equals to limit extends to a plus f of x. So if this is no, if this is false, so if this is not true, you stop. You stop and conclude. Whatever you conclude is three things. Limit does not exist. If limit does not exist, it is not continuous
and not differentiable.
and not differentiable. Okay, so you no need to, once if left hand limit is not equal to right hand limit, then straight away you can conclude, you stop.
Okay.
What if this is yes? Okay, if this is true, so then what do you have to conclude?
Function value you should find.
So limit exists. Limit exists at x is equals to a, and then what you have to check is, then after checking this, then only you have to check this left hand limit is equals to right hand limit, which is equals to the function value at that point, f of a. Okay. If again, if it is no,
not continuous.
Yeah, you will conclude that limit exists, but it is not continuous, and it is not
hence
differentiable.
not differentiable.
Yeah.
Differentiable.
Okay. So this is the second stop point. So we are going to stop here by concluding limit exists, but not continuous, not differentiable. What if this is also true, or it is yes? So left hand limit and the right hand limit both are equal to f of a. Then what we say is limit exists.
Continuous.
Yeah, it is continuous.
But may not be differentiable.
Right now we didn't bring differentiable. Till here it is continuous. Next checking will happen here. Okay, it is continuous. Okay, I agree. So what happens to this limit? Limit h tends to 0, f of a plus h minus f of a divided by h exists. Exists meaning the same thing. You have to check the left hand limit and the right hand limit. If both are equal, then the limit exists. So if this is exists, okay, again, if this is no, if the limit does not exist, we conclude limit exists, it is continuous, but not differentiable. Okay, so what I mean is existing means, again, you are checking for this is equal to limit h tends to 0 plus f of a plus h minus f of a divided by h. These two are equal or not. If no, it is not differentiable.
Okay.
If yes, again, you stop here. So this is the third stopping point. So if yes, what we will conclude is limit exists, it is continuous
And differentiable.
as well as it is differentiable.
Okay.
Okay, then you stop. So this is the some kind of algorithm. Flow chart, yeah.
Okay.
Flow chart kind of thing. This is how you can go. And always remember, limit, no limit implies not continuous, implies
Not differentiable.
not differentiable. And the other thing is also there. If it is differentiable, implies continuous, implies limit exists. Okay.
Excuse me, sir.
Yes, sir. Thank you, sir.
Yeah.
Sir, we want to share a one technique. Can I ask, sir?
I want to share or you want to share?
Sir, I want to share.
Yeah. What is that?
In different, sir, somebody is confused that the function is differentiable, then the function is continuous or not. Then we assume that the function is continuous. We assume that the student is passed in 10th class. The student is passed 10th class, we comparison to continuous, and differentiable, we assume student passed in 12th class. Then the student is passed in 10th class. Student may be passed in 12th class or not. As well as function is continuous, then the function is differentiable or may not be differentiable. And the
So, sir, the
student.
Go ahead.
Yeah, go ahead.
I'm audible, sir?
Yeah, you are audible.
Sir, we assume that when the student is past 12th, we comparison then the function is differentiable. Then definitely the function is continuous.
Okay. So you are saying that limit I will give you to some 7th class, continuity I will give it as 10th class, and differentiable to some 12th class.
Yes,
right?
sir.
Ordering you.
Yes.
Okay. So if you can remember like that, it's okay.
Thank you, sir.
I hope this
thing,
will
right?
help few of you.
I mean, so that's the thing, right? Let's say at x equals to a point, if a function is differentiable, that means that function has to be continuous at x equals to a, right? And sir, another question I have. I mean, I'm not sure if that question. I mean that's important here or not. I just want to know about this. I mean, sir, you said spanning trees could be like many types. I mean, many kinds. Like we can have several spanning trees from a tree. I mean, from a given graph. So, is there any way to find how many spanning trees can we have? I mean, just asking. I don't know if that's important or not. Just asking.
Can you say it again?
Sir, Sir, I said like we have a given graph. I mean, a graph is given, and if the question is like how many spanning trees could be made from that graph, is there any short way to do it? Because it's kind of like a lengthy
No,
process.
no. There is no short way to do it. You have to follow by analyzing different kinds of spanning trees. That's it.
Okay, sir. Okay, sir. Got it. Thank you.
Yeah. But if we felt that is lengthy, we will not definitely give. Okay.
Okay, sir. Got it, sir.
Okay. Yeah. Okay. And anything else?
No, sir.
No, sir.
Okay.
No, sir.
Okay.
No, sir.
So all the very best for your exam and do
Thank
good.
you, sir.
I hope you people will do good. Okay.
Thank you, sir.
So
Thank you so
definitely
much.
good to see all of you.
Thank you
Thank you,
so
sir.
much.
All about
Thank you so very much, sir.
Yeah.
Thank you
Thanks.
so much, sir. You are so approachable to ask doubts, sir. You are so patient in clearing the doubts. You made M1 easy.
Oh, thanks.
You are the
And
best teacher, sir. Thank you so much.
so I will take this as compliments, and I will feel more happy if you guys all come out with flying colors for the end. Okay. I
This
have
session
spent
was
this
very
much time
useful.
with you guys, hoping you will learn something from me, and okay.
Sure, sir. This session was very, very
Sure,
helpful.
Okay.
Sir, we have learned not only maths, sir. There is some. I mean, seriously, sir. I mean, thank you so much. You took our
Thanks.
studies so patiently.
Oh, thanks. So we will meet you guys. Maybe I will meet you guys in stats 2 or MLF. Okay, I hope you guys. I will meet you guys there.
So you take stats too?
Yeah, I take stats 2, and in the next coming terms, I will take MLF also.
Okay. Great. It'll be great, sir. Thanks.
Thank you, sir.
Thank you, sir.
Good night, sir.
Good night, sir.
Thank you, sir.
Thank you, sir, and good night.
Thank you, sir.
Bye, sir.
Hello. Okay. Host, you can end the session. Okay.